Hello everyone, very good evening to all of you. Some of you are writing I have not started. Don't worry guys, we had an ongoing session and that's why it took us a bit late. But anyways, welcome everyone, which is this is your one another very important chapter called as chemical bonding. A chapter that has always carried a lots of weightage in inorganic chemistry, a very root chapter, basic chapter. So previously we dealt with this periodic classification of elements, and in this chapter we'll be dealing with chemical bonding. So chemical bonding, all the concepts up to advanced I'll be covering in today's session. Up to advanced we'll be covering up to 2000 this mains and advanced concept along with some problem solving, but I will also come up with the JEE main practice of 2002 to 2025, all PYQs together. So that will be happening, that session will come in next week. In this week, today's session, I'll try to cover all the theoretical concepts along with problem solving till JEE advanced level. Okay, it's an 11th standard chapter in organic chemistry, and we'll be dealing with some of the mains and PYQs thing. Okay, mains and advanced. So let me directly take you to the first part that we do not know about. Its name is chemical bond. Name itself suggests bond. Bond means bonding, getting together. So bond in chemistry, bond is a kind of attractional force that keeps two chemical species together, such as atoms, ions, molecules. So if there's a force between the atoms, it's usually covalent bond. If it is a force of attraction between ions, usually it is ionic bond. And if it's a force which acts between two molecules, it is called as van der Waals force. So this van der Waals force also is one of the we call it chemical bond only, but this kind of chemical bond is called as intermolecular force of attraction. Let's come and have the definition that it's a force of attraction that acts between two or more atoms to hold them together, and it's a union of two or more atoms involving the redistribution of the electron between them. Okay, let's have a discussion between them. So I was just telling you, let's say if two atoms are there which are bonded, so let's say a force of attraction between two atoms, we are calling it covalent or coordinate. Covalent or coordinate. If force of attraction between ions, ions as in cation and anion, it is called as ionic bond. And if the same force of attraction acts between two molecules, two or more molecules, it is called as van der Waals force of attraction, right? It's a basic idea right now we are having. So guys, I'll take you to why does this happen, like what is the requirement of this bond, that I'll let you know. But before that, we have one more interesting part that we have to know, and this is your types of chemical bond. So broadly, there are two types of chemical bond. One of them is called as interatomic, that operates between two atoms, that keeps two atoms together. And another one is called as intermolecular, that is working between two molecules. So if we talk about the interatomic, these are stronger bonds. They have higher bond energy. It requires more amount of energy to break down, which is ionic bond, covalent bond, coordinate bond, and metallic bond. These are four broadly classified number of bonds, type of bonds, which is called as chemical bond and strong chemical bond. We also have weak chemical bond. Weak chemical bonds are hydrogen bond, and we have van der Waals forces. So basically, the strong and weak are decided on the basis of the amount of bond energy. So the bond energy, if we talk about for strong bond, is greater than 100 kilojoule per mole. And if we talk about the bonds which are weak, the bond energy is lesser than even 40 kilojoule per mole. Very less amount of energy is released when these bonds are formed. So that is the main basically difference between these two. It can reach up to 200, 500 also, but depending upon the extent or nature of bond. So let us quickly learn what were these bonds, weak molecular bonds. Hydrogen bond is one of the example. Another one are van der Waals forces, ion dipole, dipole dipole, ion induced dipole, and then these are the one. So let's see why the chemical bonds are forming, why chemical bond operates, what is the logic behind the chemical bonding. Let us understand that part first. Okay. So let me give you two important reasons. One of them is to attain the maximum stability. So guys, what usually happens, I'll explain one by one. Number one, to attain the maximum stability. So let's take an example how hydrogen and hydrogen are initially infinity distant apart, and then they come closer, and they come to a distance where the internuclear distance becomes r naught. This r naught is called as the bond length. This r naught is called as the this distance over there is called as the bond length. So there these two hydrogen atoms are bonded now, hydrogen hydrogen, right? So this is the distance at distance is equals to r naught. This system has minimum potential energy, maximum stability. Everyone wants to do one thing: minimize its energy, maximize the stability. Let us understand this thing graphically. So let's say if I'm drawing a curve between the potential energy between two hydrogen atom, and this is the distance r between them. So the graph somewhere comes like this. What is this graph representing, guys? This graph has r is the internuclear distance. So there we had infinity distance. At infinity the potential energy is nearly zero because it has no interaction between two atoms. At the moment these two atoms get minimum potential energy. Where can you get the minimum? Here we are getting the minimum potential energy. So this distance is called as r naught, which is the bond length, and this amount of energy is called as bond energy, like that. Please understand this graph, very important graph. So there we had hydrogen and hydrogen very much distant apart, very much distant as in infinity distant apart to each other. But over here these two are now bonded to each other with a bond length of r naught, So this is the first logic to acquire the maximum stability of a system and minimize its potential energy. This is the first logic that we apply. Why chemical bonds are happening, why chemical bonds are being made? Because everyone wants to get stability, and in order to get the stability, the potential energy has to go to the least, and stability should be the maximum. Even if you get them more closure, even if I get them more closure, then what will happen? If we make it even more closure, there are like two type of forces which are working. So there are like force of attraction are working. Do you know what is the force of attraction? Force of attraction is, let's say this is hydrogen number A, this is hydrogen number B. So we can say that electrons of A are being attracted by nucleus of B. Nucleus is positive charge, and we can also say that nucleus of A with a positive charge is attracting electrons of B. This is the force of attraction. Then we also have a force of repulsion. Force of repulsion will be working between the similarly charged species, which is electrons of A versus electrons of B. Both of the hydrogen atoms are there, and in the similar way nucleus of A versus nucleus of B. This is the force of repulsion. So this is the basically minimum potential energy is the place at the rate r is equals to r naught, or which is called as the bond length. A bond has been made there, and the force of attraction and repulsion are become equal. If I increase their more, if I increase this, like if I decrease the distance between these two, even I squeeze it even more, then what will happen? Nuclear will start repelling each other, electron will start repelling each other. Potential energy abruptly increases like that. If you go the lesser than the distance, internuclear distance is less than the bond length, which is r naught. then immediately the bond energy will start increasing, or their relative energy of the system will start increasing, and that is also unstable. So the only stability which we are getting is at this point, where we got the R naught as the bond length between hydrogen and hydrogen. So just try to take an idea how the bonds are being formed, and then right after this I'll explain you one more part of this theory. And the another part of this theory is actually related to the noble gas configuration. Number 2 is the called as nearest noble gas configuration. We also call it as the law of octet. So this is the law of octet. So it's very easy to understand it, that whenever two atoms are there, let us suppose we talk about two different atoms. Here we have a sodium atom, we have a chlorine atom. Okay, we know the electronic configuration of sodium is neon 3s1, and the electronic configuration of 17 chlorine is neon 3s2 3p5. So this basically loses an electron, and this electron goes there and it has been accepted by chlorine. So this has become Na positive. Na positive has electronic configuration of neon, and a bond has been developed between positive charge sodium and negative charge chlorine, and this also has acquired electronic configuration of argon, and both of them are the noble gases. Both of them are the nearest noble gases. So we'll understand it even in more depth. Right now just take an example or take an idea how the bonds are being formed. So in order to form the bonds, we had two things, that electrons can be lost, can be gained, and by that ionic bond has been developed between these two, and they are right now having the noble gas configuration, nearest noble gas configuration. Like chlorine has argon near to it, that argon which has 18 electron in it, and neon has 10 electron in it. So that's a formation of ionic bond atom is there, Cl atom is there. 17 is the atomic number, 70 is the atomic number. Configuration is neon 3s2 3p5. It is also neon 3s2 3p5. Both of them are not having any inert gas configuration, but they decided this thing, that I have one electron, I have one electron. Can we share this electron mutually? Can we share this electron mutually? Like you also take my electron, and sometime I also take your electron, and let's divide one electron each with each other. So what will happen? It will acquire extra one electron. So if it acquires extra one electron, it will become argon. If it also takes the same, it will also become argon, and there will be a covalent bond between these two, and this is become argon, this is also become argon, and there is a shared pair of electrons. This is called as coordinate bond. This is called as an ionic bond. This is called an ionic bond. Did I say coordinate? No, it's not coordinate, it's a covalent bond. Covalent bond formed by the mutual sharing of electron. So guys, just take an idea, don't be in the rush, don't unnecessarily overthink on the topic as we are right now going on, because we'll come to everything and we'll discuss everything in very detail. Okay, in this whole chapter, it's a huge chapter, we'll discuss everything in detail. So these two are the basic necessities to order to form the chemical bond. The one of them was to attain the minimum energy maximum stability, and in order to get the nearby noble gas configuration. Nearby noble gas configuration, wasn't it over here? These are the two things. Number one, to gain more stability, least energy. This was the first logic we applied. And number two, to attain the nearest noble gas configuration. To attain nearest noble gas configuration. That's why the chemical bonds are formed. So anyways, now we have come to this part that chemical bonds are formed anyhow. But what were the theories given by the scientists so that we already reached to the milestone of knowing the chemical bonds very much in detail? Let us suppose first, what did someone say about how chemical bonds are formed? So the very first theory, that was a remarkable theory we know, came called as the law of octet or octet theory or Lewis octet theory. This is called as Kossel-Lewis approach, also called as octet rule. Now let us understand what did octet rule say about chemical bond formation. So we have a very simple definition. To acquire the inert gas configuration, and not just in the inert configuration, we also must write it nearby noble gas configuration has to be applied by either losing electron, gaining electron, sharing electron, whatever it is possible, they are doing it. This is called as the Kossel-Lewis approach, that every atom is unstable and it wants to attain the nearest noble gas configuration, which are supposed to have the least reactivity in the nature. They are supposed to have or exist in their inert form only. So that's why every atom wants to attain its configuration so that it can also become stable relatively, fully filled configuration of S2 and P6. So this is called as the law of octet. As I gave you one example about sodium, how sodium is converted, completing its octet. And octet, what is the meaning of octet? First of all, what we are trying to say octet lots of time, but what is the meaning of octet? So an octet is the NS2 NP6. Okay, what we are saying, a octet NS2 NP6, that means valence electrons are 8. 8 valence electrons is called as octet. So let's start it. Let's start first of all discussing about the Lewis structures. Lewis structure. What is a Lewis structure? So guys, Lewis structure is a very simple structure of an atom, in which an atom has to be represented using its valence electron as a dot. So take an example, let's say hydrogen. Configuration of hydrogen is 1s1. Outermost electron is just 1. So simply hydrogen with the symbol H and with one dot. This is called as the structure of Lewis dot structure of hydrogen. Helium, I'll put 2 dot because configuration is 1s2. Hydrogen, helium, lithium. Lithium has configuration of 1s2, 2s1. Valence electron has to be written. Only we have to take what? Valence electrons. So how many valence electrons are there? 1. Beryllium, 2s2. We don't need to take 1s2. Only need to take the valence electron. So we'll be showing 2 dots over here. We have boron. Why 3 electrons are there? Because the configuration is 2s2, 2p1. 3 valence electrons. Carbon, 2s2, 2p4. How many electrons are there? 2s2, 2p2. 4 valence electron. So carbon should have 4 valence electron. And then nitrogen, 5, oxygen, 6, etc. So that's how we make their Lewis dot structure, by properly providing them dots which are nothing but the number of valence electrons. Next is the selection of central atom. So Lewis dot structure for elements is very easy to write, because we just supposed to need to write down just the atomic symbol along with the valence electron. But what if I'm talking about a molecule? How can you write down the structure of a molecule unless you know about anything? So you got to first decide the central atom. Okay, central atom is first of all very much decided. So let me take you to some examples. Let's say NH3 is one example. CH4 is another example. Carbon dioxide is one example. Hydrogen fluoride is one of the example. Not hydrogen fluoride. Not a good example basically to pick, because both of them are terminal, none of them is central. So we are picking the central. Sulfate ion, let me pick. Manganese permanganate ion, XCO2F2. Phosphate. So just randomly picking some example in order to explain you what is the meaning of central atom. A central atom is that atom which either has the higher atomic mass, it has a tendency to form multiple number of bonds so that it can be fitted into center. Hydrogen can never become a central atom, because if hydrogen is there, it can only form one bond. And a central atom supposed to make lots of bonds, okay, not just one, because if something is making only one bond, it's a terminal atom. It cannot be considered as a central atom. We also have the highest atomic mass, least number should be there of that atom. Like hydrogen cannot become, least number is of nitrogen. Nitrogen is the central atom. Carbon is the central atom. Carbon is the central atom. Sulfur is the central atom. Phosphorus is the central atom. Xenon is the central atom. Manganese is the central atom. So this is how we predict it, but it is again not a very hard and fast rule, because some rules can basically contradict over here. Let me give you one example. Atom with the largest atomic size is also taken as the central atom with the least electronegative. Now let me take you to one example. Let's suppose the example says we are right now having OF2, or let's suppose we are having H2O. So in H2O and OF2, both of them have oxygen as a central atom, but fluorine is more electronegative than oxygen, and hydrogen is less electronegative than oxygen. But it's saying that central atom should have lesser electronegativity. Over there we already have oxygen with the higher electronegativity, but there is certain things that we have to apply, which is a central atom should be able to form more than one number of bonds, should have higher atomic mass, should have tendency to form multiple bonds as well. Okay, should have multiple bond tendency to form, just like in carbon we have it. See, carbon. And then it should have vacant orbitals, so that it can accommodate more number of electron from other atoms to form the bonds. And hydrogen, fluorine can never become the central atom. So if we talk about the HF, so we say none of them is central atom. Both of them are terminal atoms. None of them comes to the center. So let me again reveal this part, that this is a theory that was given by Kossel and Lewis, and this is something based upon the basic postulates, not very strict and straightforward, and not very hard and fast rule is there. Yes, we can easily identify the central atom. Even if I give you a very complicated example, you can still identify the central atom. There is also a possibility that in a particular molecule there can be more than one kind of central atom. Just like if I have K2Cr2O7, then 2 Cr atoms will be working there as a central atoms. Okay, so it all depends actually. Now I'll take you to the another step of writing down the Lewis dot structure. The third is placement of oxygen. So see, these are all basics. Those who are right now in 11th standard and preparing for the 2026 exam, or those who are right now in 12th standard or droppers are watching to me, I would like to give you one suggestion, that if you want to ace this chemical bonding topic or this chapter, you have to start focusing from this topic itself. This is called as Lewis dot structure. Try to make lots of Lewis dot structure. Get to know about all the possible molecules and write their Lewis dot structure. I'll give you a few of the examples. I'll also give you some homework. But yes, you got to be very perfect writing of the electronic these structures, because these structures are the fundamental of most of these stories that we are going to cover in our upcoming session, which is like Valence Bond Theory, which is like molecular orbital theory, VSEPR theory, hybridization theory, and from that only we get to know the idea of the how to draw the geometry of a molecule. But if we know it from the beginning of itself, that is your Lewis dot structure, then it will be very much helpful to us remembering all the structures and how to write it. Then placing of oxygen is pretty simple, guys. If you have oxygen as terminal, if oxygen is coming at terminal, that it will be definitely having a double bond. So like CO2, this is a molecule CO2. What is it? It's a terminal oxygen. Similarly, let us suppose if it has only one bond is there, then it will be with a negative charge. Correct? Oxygen with a negative charge will always come at a terminal bond with a single bond. See, everything is written over there very easily. And it can also be there as a central atom. So let's say OH2 is there, water molecule is there. So there it will be single bonds will be there. Okay, and this is called as non-terminal. This is not non-terminal. In fact, it's a central atom right now. Then if there is a positive charge, at the cation, then it should be coming at the central atom. And if negative charge is there, it should come at the side atom. So let me give you an example. One of the example might be ammonium ion. Another could be the carbonate ion. So what I'm trying to say, that if a positive charge is there, it usually written down at the center of the central atom. And that's how the bonds are formed. Carbonate, you also see C double bond O negative, O negative. So terminal atom will have the negative charge, terminal atom with negative charge, and over here is central atom with positive charge. So these are the general ideas, general basically rules to follow in order to write down the Lewis dot structure. But again, I said, okay, this is already one of the theory. It's a possibility that some central atom might be having a negative charge or side atom might be having the positive charge. It's also possible. But again, Over here, just we are taking some basic tips how to write the structure, and then we are following it. Then next is, depending upon the number of 2, 4, 6 shared electrons, double triple bonds are formed. So this is saying that, let's suppose we are now having hydrogen. So H2 is there. Okay, I'm showing you some of the Lewis dot structure. Everyone, please focus. Please stay focused. We have H2. Give me a sec, guys. I got an important message to forward. Allow me a sec. Sec. H2. So we have a simple structure. Hydrogen has one. This is how hydrogen is written down. One electron is there in the outermost shell. So one electron is mutually shared, becomes one covalent bond. That is how it is written. Next. Yeah, I was explaining one concept over here, that how we make the Lewis structures. Let us suppose the example is H2. So in H2 we have one electron shared between these two, and this is an example of saying it is a single covalent bond. It's a single covalent bond. Covalent bonds are formed by mutual sharing, and all the theories which we are right now studying will be accounted for the covalent bond formation only, like valence bond theory, molecular orbital theory. Every particular theory accounts for the covalent bond formation only, because the easiest bond formation is between the cation and anion. A cation is a positively charged species, anion is a negatively charged species. They two will attract each other all the time. So there is no particular definition required for this bond called as ionic bond. But always there is a difficulty to understand the covalent bond. And covalent bond, now we just discussed that it is formed by mutual sharing of the electron, as I took the example of Cl2. In a similar way, right now we're having an example of hydrogen. So take an idea how the covalent bonds are formed, and this has been explained using this theory called as the valence bond, Lewis structure. So let's say another example is oxygen. How many electrons are there in oxygen? Sir, 1, 2, 3, 4, 5, 6. And another oxygen, 1, 2, 3, 4, 5, 6. So if we notice the structure carefully, and let's say we have this structure with us. Let us notice this structure. One oxygen can take the 2 oxygen from another. 2 oxygen can also take the 2 electron of another, and that's why it has also has 8 electrons in its valence shell. It also has the 8 electron valence shell, and 8 electron in valence shell is an example of nearest noble gas, that has been neon. In the similar way, it has acquired a configuration of helium. It might not be making an octet, but it is forming a duplet. So how to represent this structure? How can we represent this structure? This structure will be every 2 electrons which are shared will give you a single bond. Every 2 electrons. So how many electrons are shared? 4. 4 means there will be a double bond over here. Remaining number of electrons will be presented over here like this. These electrons which are participating as in bonding like this, these are called as shared pair of electron. What we call them? Shared pairs of electrons. And how many shared pairs are there? Actually over here 2. So how many shared pair of electron can you see? The shared pair of electrons, it's a pair I'm talking about, it's just 1. It is also equals to the number of bond you are making. Then these electrons which are remaining over there and not participating in the bond formation are called as the lone pair of electron. Lone pairs of the electrons. Okay, let us take one more example. Nitrogen. These all are the homoatomic molecules. So, and this bond formed is called as double covalent bond. This is called as double covalent bond. Now we have nitrogen. How many atoms are there in nitrogen? 2. One nitrogen with 3 electrons, like 5 electrons in its valence shell, represented like this. What I can observe is this, that one nitrogen, after accepting 3 more electrons from the another one, has acquired 8 electron each, and now octet is completed. This completion of the octet will give you a structure like this, triple bonded and 2 lone pair like this. So this is how it is represented. This is called as a, we call it triple covalent bond. Triple covalent bond. This is called as triple covalent bond. So that is basically some structure of Lewis dot structure. Very important part of this chapter, everyone. So I would like to again repeat this concept, and I would like to give you a few more examples so that you can become more confident and comfortable in this. Let's write some of the examples of Lewis dot structure. So you do it by your own. Let's say H2 is one example we already have covered. HCl is one example that you should know. CH4, NH3, H2O, H2SO4, sulfate, H3PO4, phosphate, H2SO3, SO3 2 negative, H2S2O. So these are some common examples I'm writing. I'm just randomly thinking, and I'm expecting you people to prepare it and get this thing ready. More and more examples can come. So these are all the examples for which you must try and understand writing the electron dot structures. I just randomly guessed them and I just made them like this. I can give you a few of the examples. Okay, let me give you a few of the examples, and I'll also give you some of the examples from which some advanced based question have been asked, not just mains, advanced based question also been asked. Okay, let me take one example. So let's say if I draw the simplest example, let me take first of video, carbon dioxide. Let us talk about carbon dioxide. So first thing, identify the central atom. The central atom will be with the less electronegativity, less number, bigger size, tendency to form multiple bonds. Carbon is the best one. So now what you do, you draw the structure of carbon, write down the valence electrons with carbon 1, 2, 3, 4. We also have oxygen. Oxygen also has 6 electrons with it in the valence shell. Oxygen with 6 electrons in it in the valence shell. Now oxygen if you count them properly, you will see oxygen has also acquired 8 electrons, oxygen has acquired 8 electrons, carbon has also acquired 8 electrons like this. So the structure, how to write the final structure will look like this. This is carbon, double bond O, double bond O. Don't forget to mention the remaining number of electrons as lone pair. Otherwise, this will not be it will not be called as a proper Lewis structure. Lewis structure contains bond pair and lone pair brought together. That is an example of CO2. Let me give you one more example, but I'll take it simple examples as of now, so that we can make number of bonds also. We know how to draw the structure, and then at last we will also understand about coordinate bond and modern ways of writing the coordinate bond. Let us take one more example. Let's say this example is ammonia. So in ammonia we have nitrogen with 5 electrons like this. We also have 3 hydrogens, 1, 2, 3. We also know that hydrogen can form only one bond and it can only acquire 2 electrons. But with the nitrogen, we also know that nitrogen right now is completing its 8 electrons. Can you count these 8 electrons? These are the 8 electrons. Final structure should look like this. So this is nitrogen, single bond hydrogen, and how many lone pairs are there? 1 lone pair. It's your choice if you want to make it like this, or you can simply leave 2 electrons like that. Got it, guys? Let us take one more example. CO2 we had, carbon, then we have ammonia, and let us suppose we have one more example called as N2O. No, yaar, there will be a coordinate bond. So first of all, I have to let you understand coordinate bond, and then I'll come to this special examples. Okay. Until then, we can take some simple examples such as where octet rule is followed. That is what I'm planning to pick. Octet rule is follows. Let's take water itself, H2O. So oxygen will be considered over central atom over here. Nitrogen was here. Oxygen will be over here. So let's see oxygen. Oxygen has how many electrons in its valence shell? 6. So 1, 2, 3, 4, 5, 6. How many hydrogens are there? 2. How to represent them? Hydrogen 1, hydrogen 1. So now talking about the number of electrons we get. This has acquired 2 electrons. This has acquired 2 electrons. Oxygen also acquired 8 electrons. Octet is complete now. Let us write the final structure. The final structure is looking like this. Oxygen double bond, hydrogen, no. Oxygen single bond, hydrogen with a electron pair like this. 2 lone pairs are there, and that's how the structure is made. So guys, it's very easy to draw this structure called as the Lewis dot structure. But again, I personally want to tell all of the students who right now are watching and finding me very comfortable writing those structure. This is a message to everyone that you cannot write all the structures if you are trying it for the first time. Nobody can do it. Why am I so comfortable in it? Because I'm very much used to of it. I've been teaching for past 10 years. My experience tells me that this is very easy. But unless or until you try it for first time, you can't say these are easy. In fact, JEE Advanced has asked so many questions out of this topic. And I'll be bringing a session from 2002 to 2025 in JEE Main practicing session next week. There you will realize how many number of questions come from each and individual topic out of this chapter. This is a very important chapter. So there could be lots of exceptions also. But before coming to the exception, I would like to tell you one important type of chemical bond called as the coordinate bond. As you already got an idea about the ionic bond between the ions, cation and ion, another idea about the covalent bond, mutual sharing of the electron. Third is called as a special type of sharing of electron called as coordinate bond. So how to define a coordinate bond? Let me write it. Coordinate bond is a special type. Of covalent bond. It's a special type of covalent bond where only one directional sharing of electron pair. You know what is the meaning of electron pair? A lone pair I'm talking about. Where the sharing of, where only one directional sharing of electron pair take place. Called coordinate or dative bond. We also call it dative bond. Let's look at the example. So where we are getting the coordinate bond. Let's say we have boron trifluoride with us, BF3, F3B. We have ammonia with us, NH3, has a lone pair, it has a vacant orbital. This is the coordinate bond. But how is it formed? What is the reason behind it? That's what we have to understand on the next page. Condition of coordinate bond. Condition of coordinate bond formation. How can we make sure that coordinate bond has been formed? How is it formed? So guys, we have two things to form the coordinate bond with it. Let's say A is forming a coordinate bond with B. A is called as a donor atom. B is called as an acceptor atom. A is called as donor atom. So this is where lone pair is being donated towards B. Condition of A is it should have complete octet. If it doesn't have complete octet, why would it like to give the electron pair? Plus complete octet plus at least one lone pair of electrons. One lone pair of electron must be there. This is the condition. It should have complete octet along with one lone pair of electron must be there if it can donate it. Then talking about the acceptor. Acceptor atom must have vacant orbital. Vacant orbital to accept it, or we can say incomplete octet. Incomplete octet, or it can have vacant orbitals to accept the electron pair, right? So the finally what we call them, if donor atom, they donate, someone who donates the electron pair is called as a Lewis base. This works as a Lewis base and this works as a Lewis acid. Acceptor atom works as a Lewis acid, donor atom works as a Lewis base. This is a condition what I'm telling you, okay? So now taking to you one example, let me take you to one example. We have O3 molecule, ozone molecule. Why did the requirement of coordinate bond came from? So what I'm trying to explain is how coordinate bond is formed. Oxygen. First of all, you try to make the oxygen molecule structure. This is oxygen molecule. We just have understood. And octet is each and everyone is having complete octet. This is something with incomplete octet because this is an atom only. So right after this, what is having? This atom has a it has a condition of complete octet plus lone pair. This is a perfect condition for donor atom. Talking about the another one which is over here, it has a incomplete octet plus vacant orbital as well. Then this electron pair will be donated. This is the structure of ozone molecule. Correct? So that's how the ozone molecule is formed, O3. One of the very important part of this chapter I'm explaining you. If you crack this part, if you can understand this part, the whole theory will become very easy to you. Now I'll give you some basic information that is not available with everyone, and I can basically make sure that this is the modern way of showing a coordinate bond. So nowadays you see molecules and you don't find an arrow over there. What is the reason behind it? because that is the modern representation. So case number 1, if the donor atom is a second period element, if your donor atom is what? A second period element. Second period element, you know, oxygen, fluorine, carbon, oxygen, carbon, nitrogen, oxygen, etc. In that way, guys, if A donated by B, then it can also be written as A single bond B with a donor atom with positive charge, acceptor atom with the negative charge. So that's one of the part. Okay, I explained just one of the part I explained. Number 2, case number 2 could be if the donor atom is a third period or higher element. It's a third period element or higher period element, then what happens? Right? Sulfur, phosphorus, arsenic, antimony, selenium, bromine, chlorine, whatever it is there, but more than third period or to the third period. In that way, we have A to B can also be represented as A double bond B. Please try to understand these two, and I'll give you some example to make everything very much understandable. Okay, I'll give you one example to make everything very much understandable, guys. So that is case 1 and case 2. Now you might not be getting examples, but I will take you to some of the example. Let me take you first example for case 1. Let's say for case 1, what example can I pick? Ammonium ion, yeah, correct. Or nitrate ion, NO2 negative ion, NO2 minus ion. So no, yeah. HNO3. So HNO3, nitrogen has how many number of valence electrons? 1, 2, 3, 4, 5. Right? Hydrogen with 1 electron, 1 oxygen with these 2 electrons to share with a double bond. नहीं यार मजा नहीं आया. Not HNO3. Let me take it to HNO2. This is fine now. Okay, HNO2. So what I see is all of them are right now having a complete octet. HNO2 is called as nitrous acid. So this has a complete octet. How does it have the complete octet? See, octet is complete. Nitrogen also has a complete octet now. This 2, 2 and A 4, and this has a complete duplet. Now where should we fit the remaining? Where should we fit the remaining 1 oxygen? So guys, there is 1 oxygen. 1, 2, 3, 4, 5, 6. Now this can be donated like this with a complete octet and 1 lone pair. This is the particular structure. So how does this structure look like? Nitrogen with a double bond oxygen, single bond hydrogen, and This is not correct actually, yaar. But we can do one thing. Let it be HNO3 only. Actually, I tried to be more perfect and have tried to present the more perfect answer, but unfortunately, I couldn't make it. I am pretty much sorry, guys. I'll take one more beautiful example and try to make it possible for all of you to understand it. HNO3 is perfect example. We have nitrogen at center. How many electrons are there at the center? 1, 2. How many number of oxygen are there? Oxygen is, this one oxygen is there. 6 electrons are in the valence shell. This is one hydrogen. This is like OH bond is there. Hydrogen has already completed. What? Hydrogen has already completed its duplet. This oxygen has also completed its octet. The nitrogen which is remaining over here has also completed its so this double bond will be shared by another oxygen. 1, 2, 3, 4, 5, 6. This is also double bond over here. We have to bring one more oxygen, and octet is now completed for nitrogen also. You can check it out. Now the octet is completed. Can we see it, sir? Can we see it, the octet completion? Because 2 electrons were already there. So 1, 2, 3, 4, 5. So if I talk about the octet completion, see 1, 2, 3, 4, 5, 6, 7, 8. This is also completing octet. Remaining is one oxygen atom, another oxygen atom over here with 1, 2, 3, 4, 5, 6. This is incomplete octet. Now condition, please try to understand how this bond is formed. Look at the condition. Look at the condition. This is incomplete, and this will basically form what? Like that. It has the complete octet. This is how the structure is looking like. So we can write this overall structure as this N double bond O, one OH and one dative bond with O, which can also be written down as, this structure can also be written down as nitrogen double bond oxygen, one OH and this oxygen with a negative charge and positive charge on the donor atom. This is how we represent the structure. Hopefully this part is absolutely clear to all of you. That was a perfect example I could have made. Now I'll take you to another example. H2SO4, sulfuric acid. The structure of sulfuric acid, sulfur as the central atom, has 6 electrons in its outermost shell. So let it be 1, 2, 3, 4, 5 and 6. So guys, you see that we have oxygen atoms over here. So 1, 2, 3, 4, 5 and the same thing over here, oxygen 1, 2, 3, 4, 5. We also have 2 hydrogen atoms. One is over here. यार ऐसे क्यों complicate किया है मैंने यार? Sulfur 1, 2, 3, 4, 5, 6. Then we have oxygen. And we also have, so there we have complete octet for all the species. Can you check it? So hydrogen has a duplet complete, hydrogen has a duplet complete, oxygen has an octet complete, oxygen has an octet complete like this. Now coming to the sulfur, sulfur has an octet complete. See 1, 2, 3, 4, 5, 6, 7, 8 like that. Now everything is having complete octet. How can we fit the remaining number of 2 oxygen? So 2 oxygen will be fitted in this way. Check it out. Let us make 2 oxygen. 1, 2, 3, 4, 5, 6. So there will be one dative bond like that and one dative bond to another. overall the structure, how does the structure look like? Let us see. This is sulfur, this is dative bond O, this is dative bond O, this is OH, this is OH. This is the structure. But again, as per the modern structure, we all know sulfur, phosphorus, everything belongs to third period and beyond, and they have vacant d orbitals also, due to which they can expand their covalency and they can form the bonds like this: S double bond O, OH, OH. Now you might be wondering, sir, one bond is equals to 2 electrons. So 2 electron are here, 2 electron, 4, 8 plus 2 plus 2. 4, 4, 4, 12 electrons are here. This is a 12 electron system. How can octet can be expanded? But yes, it can take place in those kind of molecules where the central atom belongs to the third period or beyond it. So that's why this is possible. This is a complete possible structure, and this is the modern representation what you are right now facing on this board. Please try to make all these by your own. Try to be very comfortable in Lewis dot structure, because Lewis dot structures are very important. They can give you the idea of thinking how a molecule can be drawn on the paper, pen paper, right, like that. So now I'll take you to some of the limitations of this theory. Number one, duplet. You know, hydrogen, beryllium, lithium, hydrogen and lithium, they all can form only duplet. Hydrogen, lithium, beryllium, etc. can form only duplet. Take an example. BeH2. So beryllium forms hydrogen like that. BeH2 is not the correct example, and just hydrogen is the fine example. Hydrogen can form only duplet. Hydrogen can form only duplet. It cannot go beyond that. It can only form duplet. Wherever hydrogen is connected, you have find it. Hydrogen can only form duplet. Number two, hypovalent compound. Hypovalent compounds are the one which have incomplete octet. Which have what? Incomplete octet. Examples could be beryllium hydride BeH2, beryllium chloride, boron trifluoride, boron trichloride, boron etc. Boron trihydride BH3. These are the species which will be having incomplete octet. Their octet is not completed. Then hypervalent compounds are with the expanded octet. They will definitely be having expanded octet, means their outermost electrons are even more than 8, but they exist. SO2, SO3, H2SO4, PCl3, PCl5, SF6, IF7. Everywhere you can find electrons are even more than 8 for the central atom. And the last is we have odd electronic species as well. Odd electronic species are nitric oxide, nitrogen dioxide, nitrogen ClO2, etc. And the final, pseudo inert gas configuration. So I'll explain this part in the next page itself. Pseudo inert gas configuration means they do not have NS2 NP6 configuration, but they have NS2 N-1 D10 NP6 configuration. So this is called as 8 electron system called as octet, but they have 18 electron system called as pseudo inert gas configuration. Anyways, I'll let you know about every individual thing very clearly and in very detail. Now first of all, take this idea. Rest everything is clear to all of you. Boron trifluoride. You see boron trifluoride. How many electrons are there? Wait, every bond is formed by 2 electrons sharing 2 electrons. So 6 electron system is there. Or beryllium dihydride BH2 is a 4 electron system. These two are the examples of incomplete octet species or hypovalent species. They always have incomplete octet, less than valence electron less than 8. Then we have another species which had more number of electrons, such as sulfur trioxide, S double bond O, double bond O, double bond O. How many number of electrons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a 12 electron species. We can also draw this diagram, SF6. How many electrons can you see? 12 electrons. We have PCl5. How many electrons can you see? 10 electrons. We also have IF7. 7. Okay, so this is a 14 electron system. So you can check out that there is an expansion of the octet taking place. In these cases, expansion of the octet is taking place. Is it clear to all? Yeah, very much clear. So this all is an example of expanded octet. Expanded octet. Let's have some odd electronic species. How do we get the odd electronic species? So just do one thing. Count total oblique वैलेंस इलेक्ट्रॉन्स, चाहे टोटल इलेक्ट्रॉन काउंट करो चाहे वैलेंस इलेक्ट्रॉन काउंट करो, काउंट टोटल नंबर ऑफ इलेक्ट्रॉन्स और वैलेंस इलेक्ट्रॉन्स. If it comes as odd, then this is called as an odd electronic species. Take an idea, nitric oxide. So how many electrons are there? 7 plus 8, 15, which is odd. Or you can also find out valence electron, 5 plus this has the 6, 11, again odd, right? These are the valence electrons, these are the total electrons. If anything comes up as odd, this is an odd electronic species. You can draw the structure and you can relate it with what I'm trying to explain. This is nitrogen, this is oxygen, there's a double bond between them, and this is 1, 2, 3, 4, but this is having just one electron over here. What is this? This is the odd electron, right? One more example was ClO2. Cl, how many electrons does Cl have? 1, 2, 3, 4, 5, 6 and 7, just one electron. This is called as the odd electron, like that. Hopefully this part is absolutely clear to all of you. This is how odd electronic species, right? Let me take you to one more example. Nitrogen dioxide, NO2. So how many electron does it have? 2 electron. This will be shared with one oxygen. Another will be shared with a dative bond, because you all know all the electron pairs are shared over here. One electron is left there as the odd electron. So anything can be written like this. Okay, this can also be written down as N double bond O, single bond O, negative, positive, but again with a one electron odd. Okay, Now that's it. These are some number of examples with odd electronic species. Now there is one thing which is left, is the species with pseudo inert gas configuration. Pseudo inert gas configuration. So guys, we all know that some compound exists with the pseudo inert gas configuration, not inert gas configuration. So versus, let me write, versus inert gas configuration. So inert gas configuration is pretty easy to understand. This configuration is NS2 NP6 configuration. Example, every single represented element usually has this configuration, like Na plus, this has 3s2 3p, no, Na plus has 2s2 2p6 configuration, K plus 3s2 3p6, Ca2 plus also has the same, Al3 plus also has the 2s2 2p6, Cl negative has 3s2 3p6, etc. These are very simple to explain. These are inert gas configuration. But then we have pseudo inert gas configuration as well. Now what is the meaning of pseudo, that I'll explain right now. Okay, let's see. We are right now having pseudo inert gas configuration. So guys, pseudo inert gas configuration is NS2 N-1 D10 NP6, and usually this is given by all those elements, all those cations, they have D subshells in between to them. They all are considered under this category. So let me take you to one or two example, couple of examples. Let's see. This is your zinc 2 plus. Let's say a compound is there with Zn2 plus. ZnCl2 might be the compound, Zn2 plus. So the configuration will be, let me check whether we are pseudo inert gas configuration. Yes. So Zn2 plus configuration will be 3d10. Sorry. This has NS2, NP6 and ND10. That's the electronic configuration they have. Taking you to some example. This has 3s2, 3p6 and 3d10. So 18 electrons you will see. You will see 18 electrons. Right, we had law of octet and we had 8 electrons as such till now, but now we'll see 18 electrons. So those are the examples. So Zn2 plus is one example, copper plus, silver plus, cadmium 2 plus. All the compounds where these kind of cations are there, they will form this structure. Okay, they will not have complete octet. They will have 18 electrons in their valence shell, and once they are having 18 electrons, Zn2 plus, Ag2 plus, etc. Gallium 3 plus, like that. So more examples could be there, but that is the difference between pseudo inert gas configuration, and these compound also exist in ZnCl2 exists, AgCl exists, CuCl exists. All of these compound exist, right? Now this theory is completely ended from my side. Now we should start solving some questions and to get the idea. And let's see. There we have the first question: which of the following species is hypervalent? Okay, try to find out which of them are hypervalent. So we can easily see hypervalent and hypovalent as well by just simply getting the idea, like ClO2, ClO4 minus, and I think sulfate ions, these two are hypervalent. How? Because see, try C double bond O. Why am I making double bond and not getting fear of the dative bond? Because we know that chlorine belongs to third period, and even third period and more can have this higher number of double bond as well. So O negative. So how many electrons can you see? What is the system? What does it say? 4, 4, 4, 12 and 13 electron as such. Chalo. Then we have sulfate ion also over here. Try to look at the sulfate ion. So you will see it's a 12 electron species. So correct answers are 1 and 3. P. A question came in JEE Main 2018. Let's see the question. Exactly based on the concept with what we are right now studying. Which of the following compounds contain no covalent bond? There is no covalent bond as such. So it's simply metal and non-metal where covalent bond is formed. See, where there is a metal and a non-metal is there, then forms an ionic bond. It's very simple. Because metal usually contains a positive charge, non-metal contains a negative charge, and they will form an ionic bond. If metal is there, then becomes the metallic bond. If non-metal and non-metal are connected by mutual sharing, this is called as covalent bond. So rest others are covalent bond. Phosphorus, hydrogen, oxygen, boron, everything is non-metal. Okay, we have all studied about this thing in our periodic classification of element chapter. So there we can know it is K positive and Cl negative. It's an ionic bond. So correct answer should be KCl only. C. See how easy is this question. Next, number of lone pairs on oxygen atoms of ozone. Total number of lone pairs on the ozone molecule. So how to draw the ozone molecule? We have 3 oxygen atoms. We know that we can make one double bond. One oxygen molecule is completed now. One has been donated like this. It already had 3 electrons with it. And now this is how the electron pairs. So how many lone pairs can you see? Count them. Number of lone pairs. How many lone pairs can you see? So 1, 2, 3, 4, 5, 6. 6 is the correct answer. You know how to draw the structure and then you can answer it very quickly and very easily. Another question came in JEE Advanced. So even in JEE Advanced, the question came like this, that containing same type of bond between them. But guys, for this you have to first of all know their structure. And as I told you, this all comes with the practice only. Nobody can do it. Nobody can do it without undergoing the practice. If you haven't practiced it, you can't do it. It's that easy. So you have to make the practice perfectly and then only you can do it. So like say N2O4, I can draw the structure. N2O4 has a nitrogen-nitrogen bond, a double bond, a dative bond, a double bond and a dative bond. See, B3N3H6 is called as inorganic benzene. BN, BN, BNB, and there is an alternate double bonds you can make like that. So everyone which is attached to hydrogen, B3N3H6, and with a positive charge on nitrogen, negative charge on boron, positive charge, positive charge and negative charge like that. But anyways, look at the question. Question was like whether there is a repetition of the like there is a bond between similar kind of atoms. So that was the question. Like H2S2O3, you can find the same H2S2O3. Exactly like this is the structure H2S2O3. SS bond is there. N2O, nitrogen dioxide, dinitrogen oxide, nitrous oxide. We also call it N2O is called as nitrous oxide. So again there is a bond H2S2O8. H2S2O8. You might be wondering like how can I make this structure very casually, because I know these structures very well. Yeah, even with the time you will also be very much comfortable drawing these structure. I'll also give you one example when I'll be teaching you. There's a chapter called as redox reaction, in which we understand metal metal bond, metal oxygen bond, oxy bond, peroxy bond, and relatively their oxidation states as well. But don't you worry, and before that I'll give you like this is the chapter where you can explore a lot of molecules, and you can also know about their structures and how to draw them properly. Before going to that, you can bring this thing by your own itself. So B2S6 is one of the example where is no boron boron bond. Like yeah, there is a boron boron bond actually, B2S6, right? So then we have B2S6. These are called as the banana bonds, and very different molecule. But again, the question was asked like how many of them have the same number of atoms, or together they are bonded, same atoms bonded together. This is one example. This is another example. This is another example, and this is another example. So I think 4 is the correct answer. Answer will be 4. You can check it out by your own. Now I'll take you to the next part of this chapter, right after type of bonds and this very important theory that we just finished. The theory was Kossel-Lewis theory. We have another theory, important theory called as Valence Bond Theory. Okay guys, we have now entered to Valence Bond Theory. So Valence Bond Theory, these two were the scientists who introduced this concept of overlapping. They say that valence shell orbitals, atomic orbitals must come to each other and they overlap to each other in order to form the bond. How? That I'll explain. But first take an idea and then we'll see. Okay. Okay. Walter Hitler and Fritz London, these two scientists gave this theory in 1927. Valence bond theory says that atomic orbitals come closer to each other and they overlap up to maximum extent. Take the easiest example possible, guys. Easiest example could be, this is hydrogen. This is hydrogen has 1s1. Hydrogen has 1s1. This is hydrogen, and electronic configuration is 1s1. They are supposed to overlap to each other. This is hydrogen. This also has 1s1. So they will overlapping to each other, and this is how a bond is formed between them. This is called as the overlapped region. This is called as what? Overlapped region. And there is a sigma bond between them. This is hydrogen hydrogen bond. This is HH bond formation. This is now HH molecule. Now then second is resulting bond acquires a pair of electrons with opposite spin. So this is what I wanted to explain you, that let's say this is 1s1, this is another 1s1, opposite spin should be there, and the overlapped region has electron pair like this. And that's why we say that covalent bond has a directional nature, because the direction is very important to form the covalent bond. Why? So let's say this is a px orbital, then another px orbital should come only, so that this can form a bond between them. This is the bond formation. But let us suppose this is one orbital px and there is another orbital py, which are perpendicular to each other, cannot overlap each other. there is no bond formation. Like that. Nature of orbital is very important part in deciding the overlapping. So nature of orbital means what orbital is participating, s orbital, p orbital, d orbital, f orbital, and nature of overlapping is whether they are head-on overlapping is there or lateral overlapping is there. Head-on overlapping forms a sigma bond, lateral overlapping forms a pi bond. Anyways, we'll come to it and we'll understand one by one. So as I was talking about, that overlapping will be stronger in the case where closer to the nucleus orbital are there. Closer to the nucleus means 1 1 will be having higher, 1 1 1 2 2 2 2 3. We are moving far from the nucleus, the size of orbital gets bigger and the extent of overlapping decreases. Okay, so that's how the bond strength also increases. So take an idea, guys. Let's say if I ask you, okay, tell me the idea about HF, HCl, HBr and HI bond strength. So you can simply comment, sir, in hydrogen has 1s, fluorine has 2p, 1s 3p, 1s 4p, 1s 5p. The bond energy is decreasing because we are moving far from the nucleus, and that's why this is decreasing. So this is the order actually. The order of bond energy is this. This is the order of extent of bonding also, and this is also the extent of bond strength and bond energy. If the n is same, shell is same, then more is the directional nature, more is the bonding. So we can also write it that extent of overlapping between atomic orbitals is directly proportional to the directional nature of orbital. So P will be having higher extent of overlapping than SP, and we have C 2P 2P SP, and then we have SS. Similarly SP 2S, it is about the number of n should be lesser. There we have it. So let's have one question, that the correct order of overlapping extent for the axial overlapping. The correct order of overlapping extent for axial overlapping. So axial overlapping will be PP, SP and SS, because more is the directional nature, higher is the extent of overlapping. Higher covalent bond is least overlapping. Least overlapping will be in HI because this is 1s and 5p. So there's a least extent of overlapping. D is the correct answer. Then we have overlapping of atomic orbitals can happen in three ways. Okay, 3 ways as in. So you all must accept this part, that we have understood this concept in atomic structure, guys, that so let's say this is the wave function we write, plus and minus. The concept of this wave function is what? What is this plus and minus representation? What is the meaning of this plus and minus? So this means that this is how the wave function of electron wave function is working. This is psi. Let's say this is, we are talking about the px, and this is for psi px, and this is plus minus plus. So this is actually representing as the wave function. Okay, wave function, and its charge is actually representing the wave sign. Okay, so what do you think? What actually happens is, whenever we are doing two type of overlapping, a plus sign is matching with plus sign only. This is plus, this is minus, and this is plus, this is minus. So what is happening? This is called as constructive interference. we call it constructive interference. And constructive interference actually has two waves. These are the two waves, plus minus, and plus is combined with the plus of another. This is plus minus plus, like that. So that is why the product outcome will be even bigger, and that is where the bonds are formed. This constructive interference gives you a positive overlapping. It gives you what? A positive overlapping. Next is, let's say this is plus and this is minus, and we are adding or making it overlap with negative. So this kind of interference is called as plus minus plus, like that. And the another one which we are making it to overlap with is a negative plus negative, and this kind of thing doesn't let you to this is called as the bond formation. But over here the wave function will be reduced, electron density will reduce, and we can simply say no bond formed. No bond formed. And similarly over here also, this is called as destructive interference. The destructive interference will give you what? No bond. It is called as negative overlapping. This type of overlapping is called as negative overlapping. So this is the meaning of positive and negative overlapping. And let's suppose there is one more case where there is no possibility of overlapping. This is called as zero overlapping. So positive, as I told you, plus with plus is called as positive. Plus with plus overlapping is called as positive. And even if we talk about the d orbitals, this is called as positive overlapping, and this leads to the bond formation. This leads to the bond formation, that the sign of the lobes which I am taking, sign of the lobes should be the same sign of lobe should be there with the atomic orbitals which are overlapping. Negative means the sign should be opposite. So let's say if I draw the same diagram, this is a plus and this is a minus, or this is a plus, there is a minus, or this is plus minus, this is minus plus, no bond will take place, out of which no bond is formed. The third one is zero overlapping, where orientations might be different, where orientations are very different, such as we are making this to overlap with this, so there is no sense. There could be positive overlapping at one half, positive negative overlapping, this negative overlapping over there, it is called as zero overlapping. This could be this also. These all will also lead you to no bond formation. So that's how it works. Okay, this is called as the overlapping of atomic orbitals. Some of the examples are given, but we already know about it. What is this? Positive overlapping, negative overlapping, zero overlapping. So let's solve some question. Which of the following case you think bond formation do not occur? So positive and negative overlapping, this is the correct answer. This is called as zero overlapping actually. Why does this type of overlapping given over here has no bond formation? Because this is a kind of zero overlapping, and only positive overlapping results into the bond formation, not zero overlapping. Which of the following combinations are allowed? Okay, S PZ, so S is like that, PZ is this, assuming this is the Z axis, then this is possible. We have PX and PX. Let's say this is Z axis, so this is PX. PX can also take place if the Z axis is the INA. We have PX and another one is PY in the Z axis. Okay, this another perpendicular plane. This perpendicular plane will be having no overlapping because this is Z axis, no? So this is what? This is zero overlapping. This is what? Positive overlapping. This is what? Positive overlapping. So what are possible? These two are possible. So correct, D answer is correct. Let's try another question. Okay, so which of the following orbitals form positive lateral overlapping? Positive or lateral? Lateral means you're getting head-on is against each other and lateral is parallelly. So S and S never does lateral, so this is incorrect. PZ and PZ. Okay, x-axis is the molecular axis, then definitely if this is plus minus, this is plus minus, these are PZ, because the axis which you are getting is x-axis. So yes, they can undergo overlapping. This is positive overlapping. C is the correct answer. S never gives you lateral overlapping, always does head-on overlapping. PX and PX will give you what? Head-on overlapping. Like this overlapping will take place. Head-on. Then we have two type of bond formations over here. Whenever the atomic orbitals are overlapped to each other, there is a possibility of formation of two type of bond. One of them is called a sigma bond, which is formed by head-on overlapping. Formed by head-on overlapping. S always form head-on. Talking about pi is formed because of the lateral overlapping. What is the lateral overlapping? So sigma is formed by, this is lateral overlapping. D pi back bonding, d pi also takes place like this. This is also one of the similar type of thing. This is type of bonding is take place like this, overlapping. This is the type of overlapping taking place, which is called as lateral overlapping. Lateral overlapping forms the phi bond, and this is the called as head-on overlapping forms the sigma bond. So let's see some of the combinations of atomic orbital. SS bond takes place, SP overlapping takes place, PP. We already have explained this part. Similarly, pi bond we have similar kind of thing. In this, first bond always is a sigma bond, guys, and then a pi bond is formed. So anyways, we should take a sigma versus pi first of all. These are the properties of pi bond given to us. Since it's a covalent bond is formed by the sidewise overlapping of the atomic orbitals, half-filled orbital, and so please read it out. This is the difference between sigma and pi bonds. Okay, read out this difference between the sigma and pi bond, and then we'll read out everyone and we'll try to check out everyone in order to explain some of the examples. Okay, sigma bond, pi bond, how are they formed? So during sigma bond, either a hybrid orbital takes place or pure orbital takes place, but this is because of the head-on overlapping. It can exist freely, like first sigma bond is formed and then pi bonds are formed, but sigma bond can be formed freely. No pi bond can form freely. First sigma bond has to be formed and then only pi bond is formed. These are stronger bonds. These are relatively weaker to the sigma, and sigma bonds are formed first when the interaction takes place, and then pi bonds are formed. During sigma bond formation, only sigma bond is formed during the bonding between two given atoms. No idea what is it saying, but they are also known to have cylindrically symmetric, and there is no symmetry in the pi bond. So let me take you to some examples also, and let me take you to some very easy formulation. How can I identify number of sigma and pi bond? So whenever you see a single bond A is there, we all know right now we all are talking about what? Covalent bond theories only. Valence bond theory is for the reason why the covalent bond is taken, how the covalent bond is formed. This is what it tells you. This is valence bond theory. Even in the valence bond theory, in molecular orbital theory, in VSEPR theory, everywhere we discuss about the covalent bond. This is A sigma bond A, this is B double bond B, this is C triple bond C, and there's like D tetra bond D. So let me explain each and every one by one. If one bond is there, guys, this will always be sigma, just 1 sigma 0 pi. Two bonds are there, 1 sigma 1 pi will be formed, so 1 sigma 1 pi. Sigma will always be 1, rest all will be pi, so this is again 1 sigma 2 pi, and there not possible. No 4 bonds are formed between two atoms like this. Correct? So let's see, there are some examples. CH2Cl2. So you first need to know what structure does it recommend. CHClCl like that. So how many sigma are there? 4 sigma 0 pi. Correct? Let's see, this is an example. So this is CH3. This has to be elaborated like this. CH, H, H, C, H, double bond C, H, single bond C, triple bond C, H. So this is sigma, pi, no pi takes place before sigma. So this is sigma, pi, sigma. This is sigma. So now tell me, sigma are how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 sigma. How many pi? 2 and 1. 3 pi bonds are there. This is how we identify. See how easy is this? We all know how this structure look like, and then we have to do. Anyways, guys, I forgot to mention this part here. There is a huge event ongoing in Unacademy on the 1st of this March. So don't you miss out this opportunity, everyone. Please go there. JEE Nexus by Unacademy. JEE Nexus by Unacademy is our channel where we are bringing the celebration. 1st of March, Aram 2025, India's biggest event that we are having for all of you, where you can find top educators, top students, their success journey can be revealed. So many offers will be there for the student if they want to join Unacademy for their upcoming journey. Please go here and click on the notify me button. Okay, click on the notify me button. Notification is on there. Okay, on the home page itself you can get this notify me. Now let me come back to my topic. So that's how we do. Okay, there is another question, that how many sigma and pi bonds are there? Sigma and pi bonds are there in the benzene molecule. So you can know what is benzene molecule. Benzene look like this, but actually this is benzene is C6H6. The correct representation or one of the resonance structure is looking like this, and this can also be written down as C double bond, double bond, double bond. Everywhere it is hydrogen. So how many sigma bonds can you see? 1, 2, 3, 4, 5, 6, and these 6, 12. Pi, 1, 2, 3. So how is it? 12 and 3. B. If the internuclear axis is Y, then pi bond is formed by. If Y is internuclear axis, then PX is correct answer. S will never give you lateral overlapping. PY will be like 0 overlapping, 0, and PY will be sigma bond formation. So this is A is correct actually. Which of the following overlap is incorrect, assuming Z axis to be internuclear axis? Which is not correct. So 2py pi bond is correct. PZ is sigma is correct. PX pi to X is correct. 1s and 2py pi, it can never be formed. S always does head-on overlapping. Always does head-on overlapping. So never forms a pi bond. So correct answer should be what? D. Only D. Ozone molecule contains how many sigma and pi? This is the ozone molecule with a plus minus symbol. Sigma 2, pi 1. 2 and 1 is the correct answer. 2 sigma 1 pi. 2 sigma 1 pi. 2 sigma 1 pi. D. So now there are some limitations of valence bond theory. Why this theory is very much limited and doesn't have any extension? Because there's a lots of assumptions are made in this valence bond theory. Like we are assuming a lot of things, as we have seen, the direction of overlapping, then lateral, it should be front on overlapping, and we also assumed that let internuclear axis be Z. But anyways, it also failed to explain the coordinate bond formation because it always includes the half electrons. The assumptions, it supposed made that halfly filled orbitals are allowed to overlap to each other with oppositely spin of electron. So that is an assumption, unnecessary. It also failed to explain the bonding of metallic bond, odd electronic formation, interstitial compound, etc. It can't explain the paramagnetic behavior of O2, which is explained by molecular orbital theory that we'll study with this extension of the class, explained by molecular orbital theory. Then it couldn't explain the equal bond lengths of CH in CH4 molecule and doesn't explain the geometry and shape of the molecules. So that is the limitations of VBT. So guys, we do not have too much of the applications of VBT as such in chemical bonding, but yes, we'll try to cover a few examples so that you can also become comfortable how these bonds are formed. Okay, let me take you to some examples. Okay, so let us suppose one and last example I'll use, and then you can relate how chemical bonding or how this bonding of valence bond theory is not very accurate. So guys, you all know about methane molecule, CH4, we call it methane. So methane molecule is supposed to have all four chemical bonds with equal bond parameters, bond length, bond energy, everything is very much equal. So all 4 carbon hydrogen bonds are identical. Practically, experimentally it has been measured. Experimentally this has been measured that all the 4 bonds are identical. So if all the 4 bonds are identical, then can VBT explain it? Then let us suppose carbon with its ground state configuration of helium 2s2 2p2, then this is called as its ground state. When these 4 hydrogen will approach, it will go to the excited state as helium 2s1 2p3. This is called as the excited state. Now right after its excited state, we reach to this configuration that there is one s orbital, 3 are the p orbital, which are gonna to be overlapping, which are definitely gonna to overlap with 4 hydrogen. These are 4 hydrogen atoms, and these overlapping will take place. So this is how this overlapping will let you sigma, 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 and sigma. 4 sigma bonds will be formed. But can you see that one bond over there? This is 1s1, 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 1s1. One bond is ss sigma bond. But so one bond should be weaker than other 3. This is the failure of valence bond theory. This is where the valence bond theory failed. Valence bond theory could not explain why these all bonds are not identical. So for this, in this support, we require another theory called as hybridization. We'll come to another theory called as hybridization. This is your hybridization. So from hybridization I'll start, but I'll like now take a break. So go there where we should go. Yeah, I think I must come over here and so right now go there and click on the notify me button. And we right now are having a small break, 15-minute break, and we'll join soon. So time's up, guys. I'm back. Hopefully, you all are back as well. That was a 15-minute time period we gave. Now, let's start it from the failure of VBT. So, Valence Bond Theory is quite good theory, explaining most of the concept of formation of a covalent bond, but it failed anyhow to explain so many bigger or in-depth concepts of bonding. So from here we'll be moving to the another concept called as let's go. So first of all, let me talk about hybridization. Okay, what is the meaning of hybridization? So I would like to explain this same example only where did VBT fail and where hybridization comes and plays an important role. So VBT failed because VBT could not explain the all 4 carbon hydrogen bonds in methane are equivalent and identical, but that is what has been explained by the hybridization. How? Let me reveal this part. So as we were discussing, now I have come up with the concept of hybridization. We were discussing about the methane molecule in which carbon atom being the central atom has an electronic configuration of helium, valence shell electronic configuration 2s2 2p4 2p2. This is called as GS, ground state. This is called as GS, ground state. Then one electron goes and jumps to the higher state in order to make availability for 4 another hydrogen atoms coming and making a bond with them. This electron goes there. This becomes 2s1 and 2p3. These 4 are right now present in excited state, and these 4 will require 4 another hydrogen atom to overlap with. So these orbitals 1s and 3p go for the overlapping, or we can say intermixing of the redistribution of the energy. Intermixing of the atomic orbital takes place. This process is called as hybridization. In this process of hybridization, you receive 4 1s3p, so sp3 hybridized orbitals. So do you know how these 4 hybrid orbitals look like in atmosphere or in 3-dimensional space? This is how they look like. This might not be the exact representation, but there's a bigger lobe, there's a smaller lobe. This is how they look like. Take the bigger lobe only as of now. 4 hydrogen atoms with 1s1, 1s1, 1s1 and 1s1 will come up over here. This is the sigma bond. What is the name of this sigma bond? This is your sp3s sigma bond. 4 sp3s sigma bonds are identical. Their bond length, their bond energy, their every parameter is now identical, and that is what has been explained by the hybridization. That is the failure of valence bond theory and bringing new theory in the account called as valence bond theory. Now I'll explain you what valence bond theory is, how does it work. Okay, so let's understand hybridization first of all. It's a process of intermixing of the orbitals of slightly different energies, not too much different, okay, slightly different energies, and that's why we only take the valence shell atomic orbitals to undergo the hybridization process. So as they distribute their energies and they form a equivalent set of energies and shape, this is what we call as hybridization. This thing is like, so let us read out their characteristics of hybridization. Number 1, that only atomic orbitals of similar energies can participate. So their delta n can maximum reach to, their delta n can maximum should be lesser than equals to 1. So like what I'm trying to say, let n is if I say that can 2s and 2p intermix, we'll say yes. Can 2s and 3p intermix, we'll say yes. Can 2s and 4p intermix, we'll say no. That is what I'm trying to say, that delta n cannot go beyond 1. Number of hybrid orbital will exactly the same as the number of mixing atomic orbital. So this can be taken as an example. For an example, some festive is coming, you are having your house renovated, so require another painting. So let's suppose you go to the market and purchase 2 red, let me purchase 2 red paints, 2 white paints, 2 red paint and 2 white paints. So what will happen? After going home, you realize that this is the worst color I have picked. This is the worst color I have picked. So this is white, white, red and red. White, white, red, red. Okay. Fine then. Now what? So red and white color is something that your parents didn't like, and you started mixing all of them and then made 4 containers of pink. And pink color was very much liked by your parents. So you used 2 different boxes and made all of them equivalent to each other, which is pink color, 4 boxes of pink color. This is exactly what hybridization means, that in hybridization, as many as number of atomic orbital participating. How many atomic orbitals are participating now? 4, and exactly 4 will be outcoming as a hybrid orbitals. Most of the hybrid orbitals are similar in shape, size and energy. And how does this appear? So guys, their structure is like this. A hybrid orbital looks like this. This is called as the bigger lobe with higher electron density. This is called as the smaller lobe with lesser electron density. The bigger lobe is responsible for overlapping or bond formation. Smaller lobe remains there. Majorly of the electrons is concised into this portion. Hybridization never takes place in an isolated atom. If you talk about carbon, we will say no hybridization. If you ask me about CH4, I will say sp3 hybridization. Hybridization doesn't take place in isolated atom. It only takes place in the in molecule or in combined state, or even in ion. Similarly, if you make your hybrid orbital, if your hybrid orbital reacts with any of the orbital, s orbital, p orbital, even another hybrid orbital, always sigma bond will be formed. Always sigma bond will be formed. You can never form a pi bond like this. There is no pi bond. There is no pi bond, and we can say no possible lateral overlapping. You cannot undergo lateral overlapping. There is no possible lateral overlapping. Because this portion can overlap. What about these? This cannot. That's it. So that is another point of hybridization. So don't worry guys, this is some basic point on this basic idea of the hybridization I'm taking you to up to. But right after this, I'll give you a very absolute method, steric number method. That is the Brahmastra of finding the hybridization. You can get any of the molecule, you can find out easily the number of hybridizations and all, everything you can do it by your own. So both the half-filled orbitals and fully filled orbitals of equivalent energy can involve in the hybridization. Not just the half-filled orbital can take place. No, not like that. Even fully filled and half-filled can also take place, can participate in hybridization. I'll give you one example. So let us suppose, let me take you one example. NH3 molecule is there. How this NH3 molecule is formed using hybridization, I'll explain it. We all know nitrogen. Nitrogen has an atomic structure, as an atomic number 7, and its electronic configuration will be helium 2s2 p3. This is s2 p3. Now how many hydrogens are approaching? 3. 3 hydrogen atoms are approaching. You cannot only take 2p, you have to take 2s also. How can we take all these? These 4 will undergo intermixing of the energy and will produce 4 sp3 hybrid orbitals of equivalent energy, of exactly same energy they will be producing. Right? So this is nitrogen. Let me show you 4 hybrid orbitals. Only bigger lobes I'm showing. Rest 3 hydrogen with 1s orbital. And there will be a lone pair. This is the lone pair I was talking about. So lone pair can also participate in the bonding. Like I have taken an example of ammonia. Got it, guys? So next point is that hybrid orbital always keep themselves apart in such a way they acquire maximum stability, least repulsion. So let's say if sp orbitals, I'm talking about sp orbitals, 1s is there, 2s is 1s is there, 1p. So that means 2 sp orbitals will be there. 2 sp orbitals will arrange themselves in such a way that they will acquire a distance of 180-degree bond angle from each other. Let's say we have 3, 1s and 2p, so sp2 hybrid orbitals will be there. They arrange themselves in such a way they acquire a bond angle of nearly 120 degree. So this is what I'm trying to say, that they maintain maximum stability and least repulsion between them. This is what they maintain. These are the hybrid orbitals and distribution of their energies. Distribution in space so that they can acquire a proper geometry. Leave everything apart, guys. I'll explain a very fastest way to learn about the hybridization and the most unique and modern method to understand about the hybridization. Hybridization, if it involves only SNP, then it will be SP, SP2, SP3. And if it involves SP and D also, then it becomes DSP2. But DSP2 and DSP3, these two will be seen in, these are seen in coordination compounds. So we will not be concerned about these all, even D2sp3. Inner orbital complexes will be seen in there. But here sp3d, sp3d2, sp3d, these all will be seen very frequently. So let me just check where to start the steric method with. Correct, it is about to come. Question: which of the following statement is true about the hybridization? Only those orbital which can be hybridized which do not differ much in energy, this is true. Which do not differ much in shape, no, it's not required. Even s orbital, p orbital, all can participate in the bonding and even in the intermixing. Do orbitals always hybridize? No, not for an isolated atom. An isolated atom and its atomic orbital do not redistribute their energies and get converted into hybrid orbital, not for an isolated atom. How does hybridization cause stabilization? By redistributing energy. By redistributing energy, they becomes very much equivalent in amount of energy. They acquire a proper geometry and become equally sufficiently distant to each other, and that is how they provide the stability to the molecule and to the system also. Which of the two type can undergo hybridization? As I told you that delta N can be lesser than equals to 1. So 1s 2p can undergo, 2s 3p can undergo, 3p 3p can undergo, all of them can go. Which of the following is incorrect about hybridization? Involves n and n minus 1. I told you delta n can be less than equals to 0. True. Hybridization takes place in isolated atom. False. This is the correct answer then. Now. The final thing that was needed, the one which we were already waiting for, it has arrived now. What is steric number method? Steric number method. So guys, there is something called a steric number, which is equals to the number of bond pair plus lone pair, okay, only sigma on central atom. So if you can identify central atom, number of bond pair and lone pair over it, then you can identify its steric number. For an example, methane, carbon with 4 hydrogen. Carbon has 4 valence electron. All 4 electrons are shared by hydrogen. 4 sigma bonds are there. The sigma bonds are 4. Lone pairs are 0. Steric number becomes 4. Let's say ammonia. Nitrogen has sigma bond pair 3. Lone pair 1. Steric number 3 plus 1 4. That's how we can find out the steric number. But again, we have to explain the steric number in more detail, and we have to understand what steric number gives you, what hybridization, and how it is managed. So let me write here steric number. Now here could be the possible hybridization. Now this is your possible geometry. This is your possible bond angle. This is your possible examples. Okay, let's try this. Let's say the minimum steric number will be 2, because it can, and central atom cannot have less than 2 bonds, right? How can you call some central atom as central atom if it doesn't make even two bonds, right? Minimum could be 2. Now this 2 hybridization will become 1s, 1p, sp. Geometry will be linear geometry. Please learn this at once only. Bond angle will be 180 degree because two atomic orbitals wants to settle themselves as this with a bond angle of 180 degree. An example could be beryllium hydride, beryllium chloride, ethine, etc. 2 should be the steric number. Okay, I'll help you to find out the steric number with some examples. If it is 3, then hybridization becomes sp3. Structure becomes trigonal planar. Trigonal planar structure is like this. Like this. Each and individual orbital has a bond angle of 120 degree, and there will be 3 120 degree angles will be there. If I count the number, 120 could be 2, this and this. 120 degree will be 3, this and this. Examples, how many number of examples? Plenty are possible. Let us write SO3, sulfur trioxide. Okay, boron trihalide, boron trihydride, or boron trifluoride, BF3, carbonate, C2H6. Plenty number of examples are there, and I'll explain how can we write them down. If the steric number is 4, hybridization sp3. No, this is not sp3, this is sp2. If it is sp3, because 3 are hybrid orbitals are there, sp2, 1s, 2p, it will become tetrahedral in geometry. How does tetrahedral orbital look like? 1, 2, 3, 4. Let me write 1, 2, 3, 4 like that. But anyways, most important part, the bond angle. This is a 3-dimensional geometry. Bond angle is 190 degree, 28 minutes. And how many such bonds are possible? 6 bonds are possible between these two, these two, these two, these two, these two, these two, like that. 6 bond angles are possible. Examples are methane, ammonia, water, sulfate, etc. So you got to know about the steric number, you will get all the idea. How to find the steric number, that also I'll let you know. But just stay tuned, we'll come to that part also very soon. So let's say now the steric number has become 5. Hybridization will become sp3d. D is introduced now. Structure will be trigonal. The shape will be, geometry will be trigonal by pyramidal. Trigonal by pyramidal. This geometry is represented like this. So there are 2 orbitals like this and 3 more orbitals in the equatorial plane. These are called as equatorial positions, and the green one are called as axial positions. Now there could be 2 type of angles. This is one of the angle. Between these two, it is a 90 degree angle. There could be another angle. Between these two and this is 120 degree angle. So there's 90 degree angles are how many? This is having 90 degree with this 3, and this is also having this 6 90 degree angle are there. How many 120 degree angles are there? 1, 2, 3. This is 3. What could be the possible example? PCl5. That's it. PCl5 is fine. It could be 6. In the case of 6, it will become sp3d2. Structure is called as square bipyramidal, or we call it octahedral. Another name is square bipyramidal, and it's a very symmetric structure. Very symmetric structure. So 1, 2, 3, 4, 5, 6. This is how it is made. This angle is also 90 degree. Always try to understand this is same plane. They are going up and down. And these angles are also 90. So total number of angles are 90 degree are how many? This top one having, see, 4 in the plane are having 90 degree, 4 90 degrees. The above one has 4 90 degrees with these planar one. This lower one also has 4 90 degrees with the planar one. So 12, 4 will be how much? 12. There will be total of 12. Example could be sulfur hexafluoride, SF6. Then if the steric number is 7, then this is sp3d3. In sp3d3, structure becomes pentagonal by pyramidal. Pentagonal by pyramidal, PBP. How's this geometry looking like? Not like that. Planar we have to make 5 actually. 2, 3, 4, 5. Then out of these 5, we have 2 more above, below the plane. So guys, this is where you will find bond angle of this green is 72 degree, and with this red one, this angle is actually 90 degree. Okay? These 5 are in the same plane. One is above the plane, below the plane. How many are these 90 degree angle? Total of 5 plus 5, 10. How many are these 72 degree angle? Total of 5. The best example could be IF7, like that. So that's it guys. This is what hybridization is all about. Once you are clear about the number of like steric number and all, then you can easily identify hybridization and respective things. Let's take one example came in IIT JEE 2012. Even nowadays also so many questions come from hybridization in VSEPR theory. So please be very aware. We have XeO2F2. We have xenon O2 F2. The only thing what we need to know the steric number. How? So xenon has how many valence electron? 8 valence electron. All the noble gases have 8 valence electrons except helium. In this helium, sorry, in this xenon, 4 electrons are shared by 2 oxygen atoms. Why? Because one oxygen atom, terminal oxygen atom, forms a double bond. So this will be like this: xenon double bond O, double bond O, like that. So this is how, only how many sigma bond it is contributing up to? 2 sigma bonds, 2 sigma bond pairs. There will be two, what should I say, pi bond pairs also, but I don't read that. Only sigma we need. Why? Because hybrid orbitals only form sigma. So this is what it is responsible for hybridization, by hybridization. If you talk about the pi bonds, if you talk about the fluorine, how many fluorine are there? 2 fluorine atoms. So 2 electrons are shared by 2 electrons shared with 2 fluorine atoms. 2 fluorine atoms form what? 2 sigma bond pair. But 4 plus 2, 6. Remaining two electrons as 1 lone pair. Now tell me the steric number, guys. So steric number will be 2 plus 2 plus 1, 5. Hybridization will become sp3d. C is the correct answer. Check it out. How do we do these questions? Very important one. Please keep on liking the session, okay? Those who are watching, please like the session. Then we have hybridization of atomic orbitals of central atom. In these all will be what? Respectively. Again the same thing we'll be doing. We have three things: XCO4, XCO2F2, XCOF. Now from here I will not write so many things. I'll do the calculation in my mind as I want you people to do by your own. Xenon has 8 electrons. 4 oxygen will form 4 bonds sigma, 4 pi bonds. Exactly 8 electrons will be consumed by 4 oxygens. So steric number will be 4 bond pair, 0 lone pair will be 4. Steric number will be 2 plus 2. So 4 bond pair. So 4 electrons are consumed over here, 2 electrons are consumed. So again 1 lone pair is left. So this will be coming up as 5. Then steric number over here, 1 bond pair is here and 4, 5 is there. So 5 bond pair. So 4 electrons plus 2, 6 electrons are consumed, are remaining with 2. So 1 lone pair is there. Total one is 6. For 4 hybridization, sp3. For 5, sp3d. For 6, sp3d2. Correct answer is sp3, sp3d, sp3d2. That's how we do. You guys need to take an idea. You guys need to know about steric number. You can identify whatever it takes. So that's it with the hybridization. Now we'll start VSEPR3. Allow me just a minute. I'll be coming back. Just into it. Just read it. Just read it. Okay. I'll be coming back in just 1 minute. Yeah, so where were we? Okay, so let me take you back to the VSEPR theory, valence shell electron pair repulsion theory. So this theory says that there are valence electrons, and these valence electrons containing orbitals, which could be hybrid orbitals as well, they all face relatively repulsions between them, and because of their repulsions only, we have to keep them according to a perfect geometry, so that contributes a particular shape and geometry back to the molecule. So what does this theory say? That the shape of a molecule depends upon the how many number of valence electrons are there, which are bonded or non-bonded around the atom. The bonded one are called as the bond pairs, and unbonded are called as the lone pair. And pair of electrons are negatively charged, that's why they feel repulsion. The order of repulsion is this: lone pair is the highest, then lone pair, bond pair, and bond pair, bond pair. So let's take an example of water molecule. So water molecule has this structure where oxygen with 6 electrons in its valence shell, 2 are shared with 2 hydrogen atoms, and 2 are the lone pairs here. These 2 are called as the bond pair. These 2 are called as the lone pair. Let's say this is theta 1, this is theta 2, it is theta 3, and it is theta 4. So applying this order of repulsion, that lone pair should exert more repulsion. So the order of theta should be, theta 1 should be greater than, theta 2 and theta 3 are equal, they are greater than theta 4. This is what order of repulsion is showing us. This point is clear. Next point. The valence shell is taken as a sphere where the electron pairs are localized on the spherical surface at maximum distance from one another. So we have to keep every electron pair as much as distant to each other, so that we can give it a proper geometry or proper structure. Now I would like to add one note over here, everyone. Note is why a lone pair exerts more repulsion than a bond pair. Why a lone pair exerts more repulsion than a bond pair? And that's why we got those angles in such a way: theta 1 was greater than theta 2, theta 3, and theta 4. Why a lone pair exerts more repulsion than bond pair? So the actual reason is, whenever we have any lone pair, let's say any element is there, A is there, A with a lone pair. The lone pair is under the influence oblique control of one nucleus, thus takes more space. That is why it takes what? More space. It moves around too much. But if we talk about the bond pair, then we will see the bond pair is under the control oblique influence of 2 atoms, thus occupy less space and exert lesser repulsion. That's why it has what? Lesser repulsion. So this is the theory of bond pair versus lone pair, which should exert more repulsion, and why I have explained it very well. So that's it, guys. Okay, I see one of the stupid student has joined us. Name is Programmer and writing that PW is way better. PW is OP. Very nice. I think somebody has asked you to do it. Why would a student do this such kind of stupidity? What's the benefit of a student? Tell me. Don't do it, guys. Okay, just stay focused, because what I'm teaching right now, it's exclusively by me only. This is what my hard work of 15 years has come up over here. It's not like that I have started from the day one I'm just teaching like this only. No, it has taken me around 15 years. Now I have qualified IIT-JEE. I qualified IIT-JEE in 2010. Now it is 2025. A plan, a mission, a vision, a location, a destination that you want to reach, somebody has already traveled 15 years back. Show some respect to your teachers. Okay, you don't have any right to say that this is better, that is better. You can't, man, because you have no taste of this. You don't even realize how much is the hard work comes with a person who's right now teaching over here. Look at this whole thing. This is all written in NCERT. Anybody can read it. When I read it very easily, and I don't get any kind of confusion while reading it. And I think the same thing, that why can't a student read and can become a genius like out of among everyone? Why can't he become the most, like the topper one of the class? But this is not possible. The experience itself says that you have to apply your hard work. You have to make everything understand in this way what a student can adapt. And that's what I keep on trying every day. Keep on trying every day. Now it has been more than 15 years, but now I feel like I'm giving some 100% of mine. I'm using some 100% and even more of that of mine. And that's why students are getting what I'm trying to explain to them. This is very easy. See, our YouTube is absolutely free to everyone. Anyone can come and can study. But serious students are very rare here. Students come, student post unnecessary thing which is not even required. These are not even students, they are just spammers. Probably the companies they are mentioning, they could be those people only, those who are unnecessarily writing the unnecessary comments. I don't give any time to them. Let's move forward. And so this is an important point I mentioned, that why lone pair exerts more repulsion than bond pair, we all come to know. Then comes the valence shell pair repulsion theory, that electron pair shell yeah. So there we start the valence shell electron pair repulsion theory, VSEPR theory. What happens exactly in VSEPR theory? So in VSEPR theory, guys, there are two things that we have to follow. The number one thing is, first of all, I'll take the steric number. Along with that, I'll take bond pair, lone pair, hybridization, geometry, shape, bond angle, examples. Okay, I'll start it from the least number of steric number, which is 2. 2 steric number, we have 2 bond pair, 0 lone pair. Hybridization will be sp. Geometry is linear. So does the shape will be linear. The bond angle will be 180 degree. Examples are very simple: beryllium difluoride, C2H2, many more. Okay, I'll write few of the examples as well. For same steric number 2, if we have 1 bond pair, 1 lone pair also, the hybridization will still be sp. The structure will be linear. Shape will be not defined. Angle will not be defined, because angle is always made by 2 lines. If there is only 1 line, 1 bond, you cannot define the bond angle. Example could be cyanide ion, isocyanide ion, nitric oxide. These are the similar examples. Carbon monoxide. Let me write their examples clearly. This is beryllium difluoride structure. Very easily, 2 electrons are there, both are shared. 180 degrees the bond angle. Talking about cyanide, and this is C triple bond N. So this will be having a negative charge. This is how the structure look like. So again, this is a negative charge with a lone pair like this. But again, we can't define any bond angle between that. These are the example. Okay. Now, let me take you to steric number 3. Bond pair 3, lone pair 0. Hybridization sp2. Geometry will be square, not square, yaar, trigonal bipyramidal, or we can call it, arey yaar, why am I writing anything yaar? It is simply trigonal planar. It is trigonal planar. So the shape and geometry, both of them will be trigonal planar. But, and the example, boron trifluoride, CH3 positive, a carbocation, sulfur trioxide, etc. Let us suppose we are having 3 bond pair, 3 steric number, 2 bond pair, 1 lone pair. Hybridization will still be sp2. The structure and the geometry will still be a trigonal planar. But now the shape has changed, and shape has become what? The shape has become a bent oblique V shape. Bent oblique V shape. Examples are SO2, CCl2 dichlorocarbene, etc. So let me reveal those examples also. So guys, if I talk about boron trifluoride, the very pretty easy to explain the structure and shape and geometry, whatever it is. But coming, and okay, bond angle I forgot, no? So there is the bond angle of 120 degree, and there is a bond angle lesser than 120 degree. How? Let me show you. Sulfur dioxide, S double bond O, and 1 is the lone pair. Due to this lone pair, this theta is now lesser than 120 degree, which was earlier 120 degree. Look at this and please understand what I'm trying to explain. Let us take it to, first of all, geometry versus shape. Geometry versus shape. Whenever it is mentioned with the geometry, so I'm trying to explain you this, guys, that geometry includes bond pair plus lone pair. Bond pair plus lone pair, but shape includes only bond pair. What does it mean? It means that there is an example of, let us suppose, sulfur dioxide. Sulfur dioxide has this structure as we just have discussed, with a hybridization of sp2. So in this hybridization sp2, what do you think? Geometry will be, including all 3 parts, will be trigonal planar. But if I talk about the shape, hide it. What is this? Angular V shape or bent shaped. That's it. This is the difference between the geometry and shape. So let's take an example. You are riding a car. You just got out of a car and you have freshly bought the car from the showroom only. You are bringing your car to the home. And meanwhile of the way, you found that there are two trucks coming from the left and right, and you try to take an overtake in the mid of these two trucks coming. Okay, mid of these two trucks coming. And due to a certain level of accident, where are like two of the side mirrors got basically broken. Now the remaining car without the side mirrors is called the car with these without side mirrors is called as the shape. But if I talk about the car's cover, the cover which is used to cover basically the car, this cover itself contains a structure, a particular part of side mirror also. Maybe the side mirrors are not even available with the car. This car cover is called as the geometry, and the car without its side mirrors is called as the shape. So this is what I'm trying to say, that whenever a molecule is given with its lone pair over there in the central atom, you got to hide it in order to find out the shape. But if you consider a lone pair also along with it, then it is called as the geometry. There is a difference between shape and geometry. Now I can take you to coordination number 4. We have coordination number 4, bond pair 4, lone pair 0, hybridization will be sp3, geometry will be tetrahedral. If there is no lone pair, then shape and geometry will be the same, tetrahedral. Bond angle will be 109 degree 28 minute. Example will be CH4, H2SO4, H2, S3PO4, and many more examples are there. Four is the static number, 3 is the bond pair, 1 is the lone pair. The structure will become SP. The geometry will be sp3. Hybridization sp3, and geometry doesn't change, it will be tetrahedral as well. But the shape this time will be changed and it will become trigonal pyramidal. Trigonal pyramidal. Bond angle no doubt will become a bit lesser than 109 degree 28 minute. Examples are ammonia, phosphine, right? Now 4 is the atomic the static number. 2 bonds are there, 2 lone pairs are there. sp3 still will be the hybridization. Geometry never changes, it will still be tetrahedral, but shape changes because of one more lone pair. The shape now has become angular, oblique, bent shaped. Theta will still be lesser than 109 degree 28 minute. H2O, H2S will be the example. Now let's check the examples one by one and their shapes also. We have methane. This is the structure of methane. 4 bonds are there. Bond angle will be 109 degree 28 minute. Ammonia is there. 1 lone pair, 3 bond pair. You know that bond pair will be squeezed down here, and the bond angle remains 107 degrees. And talking about water, the bond angle is still more squeezed because of 2 lone pair. This bond angle has now reached to 104.5 degree. So just take an idea, guys, and look at the shape. Geometry tetrahedral, geometry tetrahedral, geometry tetrahedral, shape tetrahedral, shape pyramidal, shape angular or band shape. That's how we find it. यार लग रहा है इसका पार्ट 2 लेना पड़ेगा. खो न जाए Okay, I think this is all clear till here, and if it takes more time, let's suppose, so we can convert this into 2 lectures also. We can take 2 lectures as well for this, because it's a big chapter, and there's a plenty of things right now remaining even after valence bond theory, and valence bond theory, hybridization, VSEPR theory. But VSEPR theory being the most important theory, I want every one of you to attend this class. Try to learn how I run out these all examples and questions, and please try to understand how VSEPR theory is applied over here. See, now I'll take you to coordination number 5. Oh, sorry, not coordination number. This is steric number. This is steric number 5. Then we have bond pair 5, lone pair 0. We have hybridization as sp3d. We have geometry as trigonal bipyramidal. When there is no lone pair, the shape and geometry will be the same, trigonal bipyramidal. Bond angle will be theta is equals to 90 degree and theta 2 is equals to 120 degree. Examples are PCl5, SCl5 plus, like that. So guys, what if I take out of these 4, if I take 5 steric number, 4 bond pair, 1 lone pair, the hybridization is sp3d still, geometry is tvp, shape needs to be identified using the diagram itself. Bond angle will be anyhow, theta 1 will be lesser than 90 degree, theta 2 will become lesser than 120 degree. The example will be SCl4, XCO2F2, and many more. Then it could be phi 3 and 2 and phi 2 and 3. So again this will be sp3d, trigonal bipyramidal, sp3d. Shape will be different, that will come to know, and bond angle will also come to know by that time only. But 3 bond pair, 2 lone pair, the example could be XCOF2 and SOCl2 No, 2 bond pair, 3 bond pair, 1 lone pair, fine, SOCl2 like that. And over here also this example could be I3 negative, ICl2 negative, XCF2, etc. Now guys, I'll take you to some examples and then we'll complete this part. Okay, first of all, we all must know this part, that this is called as Bend's rule. This is called as Bend's rule. The Bend's rule says that more electronegative elements, basically this is applied for steric number 5 in the trigonal bipyramidal geometry. In trigonal bipyramidal geometry, more electronegative element, because these positions are not uniform, are not symmetric, the positions are very much different. So in trigonal bipyramidal geometry, more electronegative element acquire axial positions. Okay, like all singly bonded, example halogens, fluorine, chlorine, bromine, etc. And doubly bonded substances, double bonds and lone pair. This should not be double bond, it should be multiple bonds. Multiple bonds as in double bond, triple bond, and lone pairs must acquire equatorial position. Equatorial position to basically in order to produce less repulsion or more stability. Okay, position for less repulsion, okay. So this is called as Bend's rule. Now according to Bend's rule, if let's see if I give you some of the ideas. First of the example was steric number 5, bond pair were 4, lone pair was 1, steric number was 5, then bond pair was 5, sorry, bond pair were 3, lone pair were 2, and steric number is 5. Bond pair was 2, lone pair was 3, and steric number was 5. And all right now are coming from bond pair 5, lone pair 0, steric number is equals to 5. The example was PCl5, 1 phosphorus, chlorine, chlorine. These are actually planar. So let's say this is going inside, this is coming, let us suppose, outside. So this is how this structure look like. It's been very much clear that this bond angle is a 90-degree angle and the bond angle between these two is 120-degree angle. Now I'll take few of the example from these also. So the example with 4 bond pair, 1 lone pair, I took it like 4 bonds, 1 lone pair is XgO2, F2. So 4 electrons are shared with oxygen, 2 are shared with the fluorine. Now do you remember that xenon central atom, fluorine should come on the axial position because it is more electronegative. Multiple bonds should come in the equatorial position. Like look at this guys, and 1 will be the lone pair. How easy is this? Now look at the shape. Now shape is different guys, the shape is different. The shape has become now seesaw. Seesaw. Look at its shape. The shape and geometry are the same. The shape and geometry are still the trigonal bipyramidal. Next example for this one, 3 bond pair, sorry, 2 lone pair, 3 bond pair. is XeOF2. Now look at this structure, guys. Xenon is the central atom. I told you that axial position will be acquired by the more electronegative element. Double bond O should come up this like this, and 2 lone pair will be acquired in position like this. If I hide these lone pair, I'll be getting the shape. The shape will be T-shaped. This is a T-shaped. This was seesaw. And the third one, XCF2. Check out the third one. This is xenon. Axial positions are required. 3 lone pair will be taking place of equatorial. If you hide them, it is a linear shape. It is called as linear. So this is how we write down the shape by hiding, right? Geometries will be still the same. Let's say if you are writing the geometry, geometry will still be the same. If I write the geometry, then geometry will be trigonal bipyramidal, trigonal bipyramidal, trigonal bipyramidal, and this will also have the same geometry, trigonal bipyramidal. Geometry and shape are the same. Please look at this. This is an application of, this is whole an application of Bend's rule, where what has to be applied. You might be confused, like how am I picking only lone pairs at equatorial, not taking it the axial? Because this is what our rule said. The rule, Bend's rule, said that multiple bonds and lone pair must acquire the equatorial position or lesser repulsion, because more repulsion is found on axial positions which are at the 90-degree angle, to which all the like groups are other than it are at 90-degree angle. Okay, let me take you. Sir, is there a DPP we can do after the class? Well, I'll try to give one DPP. I'll try to give one DPP, and surely it will be posted. It will be given in the our Telegram channel itself. So please join our Telegram channel. The link is in the description. By that channel only, I'll provide you the DPP. Now let's come back and join this session. Or where were we, by the way? We just have finished the steric number 5. Now let's go to the steric number 7. So we have steric number 6. 5 is done. We have bond pair, lone pair. Lone pair will be 0 here. Hybridization, sp3d2. Then we have bond angle. Hybridization is this. Geometry, octahedral. Shape, octahedral. Bond angle, 90 degree. All angles are 90 degree. Example, SF6, IF6 positive, XCO2F4. These are the example. Next could be 6 steric number, 5 bond pair, 1 lone pair. Hybridization will still be the same, sp3d2. Geometry will be octahedral only. Shape will become square pyramidal because one of the position has been occupied by lone pair. We have to remove it while calculating, while finding out the shape. Theta will be no doubt. Theta will be less than bit of 90 degree. Example could be XC और S 5 बॉन्ड पेयर 1 लोन पेयर. XCOF4, IOCl4 negative, etc. Next example is 6 steric number, 4 bond pair, 2 lone pair. Again sp3d2. Geometry nobody can change it. Octahedral. Shape will become square pyramidal. It will become square planar. An example is XCF4, IF4 negative, like that. Now let me give you all the examples related to these one, and then we'll finish up this topic. So let us have SF6 at once. So sulfur up and down, inside of the plane, 1 and 2 fluorine, outside of the plane 1 fluorine, outside of the plane 1 fluorine. This example is SF4. All the angles you find are, these are 90 degree, this is also 90 degree, every bond angle is a 90 degree angle. Then we have XCF4, so XCO. So guys, there is one lone pair, one double bond O will be in the opposite to that, rest 4 fluorine atom will be in the same plane. This has become square pyramid. And now the third one is XCF4, so 1 fluorine, 2 fluorine, 3 fluorine, 4 fluorine, and 2 are the above and down lone pairs. So these are the 3 structures where you can see this bond angle has been disturbed now. This all have inclined like now, so bond angle has become less than 90. But there we have all the thetas 90 degree only because of the equal proportion. This is 90 degree. All bond angle are 90. So that's it for the steric number 6. Coming back to our steric number 5, I forgot to write their structure and the bond angles. So now shape for this with SCl4 will become seesaw. With the XCOF2, this has become what? 1, 2, 3 T shape. Theta is again less than 90 degree. And this is a linear shape. Theta comes up 180 degree. Now comes steric number 7. Steric number 7. We have bond pair also 7, lone pair 0. Hybridization will become sp3d3. Geometry of the molecule becomes pentagonal bipyramidal. Shape doesn't change unless there is a lone pair, so it will be PVP, pentagonal bipyramidal. Bond angles will be 2 type of bond angle. Theta 1 is equals to 72 degree, theta 2 is equals to 90 degree. Examples are IF7, XCF7 positive. Another could be 7 coordination number, 6 bond pair, 1 lone pair. Still hybridization is the same, sp3d3. Geometry nobody can change, is PBP. Shape will definitely be changed, it becomes distorted octahedral. Distorted. Theta, none of the angle is 90 degree there. Bond angles will be, examples is XCF6. Oh my god, XCF6. Where did I use this example? I have wasted this example somewhere. I remember I wrote XCF6 somewhere. XCF5, XCF2 is somewhere. Okay, no, XCF6 we haven't used it. XCF6 is one such example. Now let me draw their structure and then you will come to know about it very well. We haven't mentioned the shape. Shape is mentioned. IF7. This is iodine. This is 1 fluorine, 2 fluorine, 3 fluorine, 4 fluorine, 5 fluorine. Then we have like that. This is a pentagon actually, you see. There's a pentagon we have. Pentagon and above and below. This is PBB. But what if you talk about the distorted octahedral? This is xenon, 1 fluorine, 2 fluorine, 3 fluorine, 4 fluorine, 5 and 6, along with a lone pair. So wherever you see the place, put a lone pair. This is all distorted now. So none of the angle over there is 90 degree. This is distorted. And there we end with the valence bond theory, a very important theory. And there are plenty of questions, guys. Okay, sir, what about the WhatsApp channel? We don't have any WhatsApp channel as such, but probably hopefully I'll make my own WhatsApp channel. I will try to add all of you student. Okay, just stay patient. Now let's try and solve some question and then we'll get after it. Okay, once we finish this, we'll try to take the next session in upcoming sessions, only upcoming classes. We have geometry and shape of ClF3. ClF3, geometry and shape. So guys, you all know about ClF3. Chlorine has how many electrons? 7. Out of 7, 3 are shared in bond pair, 2 are the lone pair, 4 electrons will become 2 lone pair. So total steric number is 5. So 1 fluorine, 2 fluorine, 3 fluorine, 1 lone pair, 2 lone pair. That's how it look like. So the shape, geometry, you see, steric number is how much? Steric number we can identify just by knowing it is 5. Hybridization will become what? sp3d. Geometry will become what? Trigonal bipyramidal. And shape is what? You can check it, it is a T-shaped. So where can you find the correct answer? Trigonal bipyramidal, T-shape. B. नजरों से मेरे यहाँ देखो ना खुद को जरा. Okay, let's see the another question. Let's see, this question is from JEE Advanced 2024. This question is from JEE Advanced, and the question is pretty on the same concept what we are right now studying. The question says that based upon the valence shell electron pair repulsion theory, match the xenon compounds with the list. Okay, so XCF2, guys, 8 electrons are there. 8 electrons are there. 2 are shared. So 2 bond pair, 3 lone pair. Steric number is 5. Structure is trigonal bipyramidal with 3 lone pair. This matches with 5. XCF4, 4 bond pair and 2 lone pair. Octahedral is the geometry because 6 is the this. So 2 lone pair, this matches with 3. 5 and 3. B is the correct answer. See how easy is this question. JEE Advanced 2024. Now you are cracking advanced, guys. This concept is something that is the key. If you know the concept, nobody can defeat you. That's what I want to say. There was a question from JEE Advanced 2024. You just cracked. We have a question in JEE Main 2019. The correct statement about ICL5 and ICL4 minus. You're right, guys. Let me make a shorts out of it. No, yeah, it's fine. With the correct statement out of this ICL5. So ICL5S, 7 electrons are there. 7, 5 bond pair, 1 lone pair. So octahedral geometry and shape is square pyramidal. And there we have 4 bond pair, 2 lone pair. It will become square planar, square pyramidal and square planar. So this is correct answer B. Let's see another question. We have plenty of similar questions over here. IF7, ICL4 minus, everything we know. Okay, so number of lone pair we have to find out. So IF7 is 7 bond pair, 0 lone pair. So this will be answered as 0. ICL4 minus 7 plus 1, 8, 4 bond pair and 2 lone pair. 4 electrons are there, 2 lone pair. So 2 lone pair will be matched with 3. So 4 and 3. And this is correct. Option number 2. See how easy. Challenge. Okay. So guys, if your concepts are very clear, okay, if you have the all concepts clear and you have the depth of the concept, you can crack any exam you have. That was a question from JEE Advanced 2025 which you just have solved in 5 seconds. Let's see the another question. नजरों से मेरे जहां देखो ना खुद को जरा देखो ना. Another question from JEE Advanced 2015. The triatomic molecule, number of total linear molecules with no hybridization from the central atom does not contain any d orbital. Okay, well, there should not be any hybridization with d. So BeCl2 linear and sp. This is sp hybridized linear. This is our correct answer. N3 minus. So this is BeCl2. N3 minus azide ion. Linear. Sp. N2O. Linear. Sp hybridized. NO2 positive. Again Sp linear. O3 non-linear. SCl2 two lone pairs non-linear. ICl2 three lone pairs. But this is sp3d, even I3 minus as well. sp3d, XCF2. Now check out the correct answers which are linear as well as containing no d. This is 1, 2, 3, 4. That's it. 4 is the correct answer, I guess. Rest of them are containing d orbitals. JEE Advanced 2016. We have another question from JEE Advanced 2016. The compound with two lone pairs of electrons on central atom is or are with compound with two lone pair of electron. So we have, I think I can directly pick this answer. This is the correct answer because Cl has 3 fluorine atom on axial sides, 1 at equatorial, 2 are the lone pair, 7 electrons are in total. The correct answer will be B. So we have plenty of other questions as well that we will try in our doubt solving paper. Okay, we'll do it in doubt solving only. Let's come to the another topic from here. Thank you, I'm fine name. We have next topic as a just an application. These all topic which we will study from here will be an application of VSEPR theory and hybridization theory. So one of them is dipole moment. First of all, I have to understand what is the meaning of a dipole moment. So guys, let us suppose we have a molecule called as HCl, hydrochloric acid, and its molecule has chlorine which is more electronegative while hydrogen being less electronegative. The electron pair which is shared between them will be shifted towards chlorine, acquiring a partial negative charge and a partial positive charge on hydrogen. Since this hydrogen contains a partial positive charge, it is called as electropositive. It is called as electronegative because of the negative charge. But this is what we call it as a polar bond, and polarity of this bond is shown from less electronegative to more electronegative. This is called as the dipole. That's what we call it as a dipole, pointing from positive to negative. its magnitude is given by Q into D. So dipole moment is represented as mu, and its magnitude is given by charge into distance. So this is called as a dipole moment, and we also call it as a bond moment. So let us suppose if we have nitrogen, hydrogen, 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 and like this. So if we are picking this part, this nitrogen, hydrogen, we will be calling it as a bond moment. And overall bond moment, so look at the directions of all. This has a direction of lone pair toward itself. This is the direction of towards nitrogen. This is the direction. This is the direction. These are all the bond moments. So overall, this is where the direction is coming, is called as dipole moment. This is the overall dipole moment. Bond moment is for one bond. Dipole moment is for the all molecule, complete molecule. If any molecule is a diatomic, only contains 2 atoms, then its bond moment and the dipole moment are the same. Bond moment and dipole moment will be the same. Okay, so guys, how are we gonna to basically find out its mathematical value? So if we talk about its SI value, so SI unit will be Coulomb into meter, because this is Q into distance, right? So Q into distance will become what? Coulomb meter. And in CGS we have its ESU, electrostat unit, into centimeter. ES is centimeter. Apart from these two, we have one more unit called as conventional unit. Conventional unit is capital D, dBi. Capital D is called as dBi. So how dBi is connected? It has been given over here. 1 dBi is 10 to the power minus 18. So 1 dBi is equals to 10 to the power minus 18 ESU centimeter, and also equals to 1 dBi is also equals to 3.33 into 10 to the power minus 30 Coulomb meter. Hopefully I'm right. 10 to the minus 30, correct. So this is how they are interrelated, but no question comes from the mathematical formula of this. Only question comes out of the this dipole, its vector direction of the dipole. Only the question comes from whether the given molecule is polar, non-polar, like that only the question comes. So let's say if there is a question, how are we going to solve this question? The question is that, okay, you can also identify the percentage of ionic character. So percentage of ionic character is mu actual or practically or experimental upon mu theoretical oblique calculated, actual oblique practical into 100. So that's the mathematical formula we use to apply in order to identify the ionic character of a compound. So let's see if we have this question with us, percentage of ionic character in lithium fluoride. So in lithium fluoride, see, this is lithium, this is fluorine, expectedly it has a minus E charge, expectedly it is a theoretically it has a positive E charge. So you can identify the mu calculated. Mu calculated is how much? Distance is also given to you. So this is charge is positive 1e, 1.6 10 to the power minus 19 coulomb multiplied by distance in 0.156 10 to the power minus 9 meter. This is coming in coulomb meter. So if I divide this is in coulomb meter. So if you multiply coulomb meter by, I'm trying to convert it into dBi. So you remember that 1 dBi, capital D is the dBi, was equals to 3.33 10 to the power minus 30 coulomb meter. So 1 coulomb meter is how many? So it will become 1 by this. Okay, 1 coulomb meter is how many dBi? 1 by 3.33 into 10 to the power 30. So this will become 3 into 10 to the power minus positive 29 capital D. Just multiply this by 3 into 10 to the power 29, then it will become in dBi. Now do it. So 0.15616, let us take it. So, 48. Let us take it 4.8 into 0.156 into 10 to the power. This is 29. 29 minus 90 is 10. 10 minus 1 is 1. So this is 1. So this is like 1.56. So 1.6 only. So let me just use my calculator for a while. हैरान मैं हूँ. So this is like some for 0.75 or it is like 7.5 dBi. This is coming up as 7.5 dBi. Now guys, you can calculate the percentage ionic character by using this formula. How? So percentage ionic character will be how much? Actual upon you found it theoretical into 100. So this will be nearby, I guess some 84% only this will come up as. Yeah, I can relate it. C is the correct answer. This is the correct answer. Now I'll take you to the application of dipole moment, how the questions of dipole moment has been asked, how to apply dipole moment. Okay, so this is the final topic for the day guys, and right after this we'll be finishing and we'll complete this remaining part in tomorrow's session. Pardon me, because this is a huge chapter and we have plenty of things remaining for this chapter. Allow me a moment. Once. Sir, Neeraj Kumar, level 1 and level 2 enough for advanced. Yes. Rest you can apply PYQs of advanced itself so that you can get the idea. कहाँ पर हो यार? आओ एक बार आओ. We have dipole moment. So you guys know that dipole moment mu is directly proportional to electronegativity. So let us suppose if I ask you for HF, HCl, HBr, HI, what will be the order of dipole moment? HF will be having higher. This is the order of dipole moment. because you all know the electronegativity of fluorine is more than chlorine, then bromine, then iodine. But we have a very interesting thing here. But if we have methyl fluoride, methyl chloride, methyl bromide, and methyl iodide, there is a difference in the calculation here. And if we talk about the dipole moment, because dipole moment is actually what? Q multiplied by D also, and this D is large for CH3Cl, and charge is maximum for CH3F. So overall order comes up as CH3Cl as the highest, CH3 fluoride, CH3Br, methyl iodide. Please learn this. This is very important data of dipole moment. This is very important data of dipole moment. Very important, as in very, very important. So let's say we have polyatomic, then we will have to consider the vector sum of the resultant. Just like take an example, all the symmetric ones like BeF2, SO3, CO2, PCl5, SF6, IF7, all of them have zero dipole moment. Why? So the net sum, this is also tracking as mu, this is also tracking as mu, overall mu net will be, this is the vector sum will be 0. Like that happens. S double bond O, double bond O, double bond O. Where can you find mu? This way, this way, this way. Resultant mu net 0. CO2 double bond O, double bond O. This one, mu net 0. PCl5, one Cl, they all will be cancelling out each other. These three will cancelling out each other. Mu net 0. So for these symmetric molecules, we always have zero dipole moment. Always have zero dipole moment. But if we have some different type of structure, then dipole moment may vary. Okay, allow me a moment, guys, and you read it out, this expression. You read out it, and I'll be joining you shortly. So guys, wherever we have the molecules with regular geometry, they all have zero dipole moment, as just have discussed about them. But yes, wherever there is a different kind of geometry and lone pair have come in the game, molecules the regular geometry, that means no lone pairs as such, they all will be having. Okay, like take an example: beryllium difluoride, boron trifluoride, CH4, PCl5, SF6, IF7, all of them will be having regular geometry, and that's why they all have zero dipole moment. But yes, there could be some more examples such as XCF4. Even with lone pairs, the lone pair will be occupying these positions, and it is a square planar structure, square planar, and that's why here also mu net will be coming up as 0. So that is a case where lone pair is given, but still it will be 0. This is happening even with lone pairs. There could be more examples. I would like to suggest you that you should draw it properly and then try to find out. Okay, so that's why we have the last and final concept to reveal here, and I'll be giving so many good examples here where you can find all of the examples will look same only. You have to tell me which of them will be having 0 dipole moment or which one of them will not be having 0 dipole. So this is a homework which I'll be continuing in the next class. This is a homework for all of you. This is your B, C, D, E, F. Out of these 6 examples what I have written, the question is, out of these, which are non-polar molecules? You have to tell me which are non-polar molecules, means mu is equals to 0. That's a homework for all of you. Now I'm signing off for today. I've been feeling bit tired, and in my next lecture, maybe probably tomorrow only, we'll continue from here and we'll try to finish the remaining part of this chapter, which is application of VSEPR hybridization in bond parameters, molecular orbital theory, hydrogen bonding. These topics will be covered in next lecture. Bye bye everyone, take care.